started shortly. presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. This show is funded by supporters on Patreon and Subscribestar. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Good afternoon, everybody. I hope everyone's having a beautiful day. I want to welcome you on to the stream here, all live. So, let me just get that open. So, let me know how you're doing in the chat, and of course, I hope you're having a beautiful day today. So, before we get started here today, I just wanted to mention a few things. So first, if you're new to the channel, be sure to check out all the other content here on the channel. I produce daily educational and entertainment content in computer science, especially. For example, last week we did a live lesson on graph traversal algorithms, which I'll be building upon today. In addition, I'll keep in mind I'll do a little bit of a primer here before we get properly started. Because all of that will be highly relevant here. So don't worry if you missed that one, that's okay. We'll be talking about anything that's relevant there, here. Okay. Other things. If you aren't already, keep in mind that at least at the moment, I'm doing my live lectures on Tuesday about this time, if not a little earlier. We started a little bit later here today. Normally I start at noon Central Time. But today I had to get a few other things sorted out. Also keep an eye out on Thursday. I also have my gaming stream or entertainment stream. So I do play games live on the Twitch, YouTube, and on Facebook as well. So do check out the links that you'll find on the channel respectively or in the description. So please check out those. There's always a good on time. Come on out. You always have a blast. Other than that, keep in mind that some of the material that is derived from today, let me just grab one quick thing here. I'm just going to grab what I need to talk about here. I assure you I'm not going anywhere. Too far, at least. If you're wondering about learning the preamble before this, or if you're interested, keep in mind that on the channel I have a series on data structures and algorithms called Advanced Data Structures, an introduction to data structures and algorithms. This book is the companion notes for that series. The set of notes are also available at the appropriate tier on Patreon and Subscribestar. So if you're curious about that, check out those respective pages, specifically Patreon. It's actually at the general support tier, which you'll get a digital copy of this book. I sign it myself. And of course, if you're looking for something to say, if you're looking for some companion notes to help learn the material that is on the channel, this is a pretty good place to start. And it's rather affordable. I always strive for affordability with my material. That is, in fact, one of the main missions of what I am doing here. That is what delineates it from most other options out there. One other thing before anything, of course, tell your friends to come on out. Make sure you subscribe, follow, and of course, you gotta crush that like button. That's what they tell you to say. Who's they? I don't know. But of course, let me know in the chat. One other thing. Oh yeah, I always have so many things. And one more thing. If you're wondering, the chat is visible between parts of the lessons today. So if you're wondering why, for example, you can't see the chat or hear it over the stream during the main lessons when the chat disappears, it's because during those times I can still hear it and see it. I have a display over here. If you're wondering where my eyes are going, I have a chat just over here. So if you're wondering why, say I want to see what's in the chat, it will be on the screen after in between there, I'll be addressing any more sophisticated questions. If anyone has any more like complicated questions that aren't just simple things for me to address, I'll address them at that time. Likewise, like I said, if you type something in the chat, especially on Twitch, I will hear it. But also, I must stress that regardless if you're watching this on YouTube, Facebook, or Twitch, it'll appear in the chat, and I have visibility of the chat. So if you have questions while you're learning or watching, you can catch that stuff. I'll be keeping an eye out for this stuff. So I'll sometimes ask questions and see what I like to keep things really highly interactive here. So other than that, of course, if you have questions after this, say if you're watching this in the future, just put your question in the comment and I'll usually be pretty happy to address it, okay? So anyways, the main things that we're going to talk about here are applications of graph traversal algorithms and some of the properties. Now, I won't be talking about an exhaustive list of all of these things. Instead, I'll be focusing on a subset of them. And whatever stuff I don't cover, I'll eventually cover, or if you're interested in that, let me know. Let me know. So I'm going to start by talking a little bit about some, I would argue it's a bit more review of just what we talked about last time, because this will be highly relevant for today. So I'm going to first just kind of give you this, and then once I get into the actual lesson, the main thing that we're going to focus in on, I will take the chat away off the screen. Just keep in mind, like I said, I will still be able to see the chat, and also I'll be able to hear it. So if you have questions or comments, or you want to say your favorite line of the day, go for it, please. Please. This is a fun place too. It is also learning. It's learning. And listen, if learning ain't fun, it's not going to be a good time oftentimes. Not everything can be fun, but most certainly I try my best. Hey, so let's talk a little bit about kind of the preamble for today. So in previous lessons, we talked about what a graph is. So let me just first remind you what that is. So a graph consists of vertices and edges. So usually if I give you a graph G, it is a pair for which the first part of the pair is a set of vertices. Think of these as these dots here. Each one of them may have a label or may not. Usually in the context of computer science, normally these are indexed or have a name. They may be two separate entities, by the way. And as a set of edges, these connect the vertices. Sometimes vertices are called nodes. So these dots here, these are the nodes or vertices. And the connections between the dots, or what we call nodes. So, let me just note those. So nodes, vertices. So I must stress that this is plural. So all of these are nodes and vertices. A singular is node, and singular for vertices is vertex. It's not vertexes. Please don't make my brain melt. It's horrible when I run into it. So these are called edges. Sometimes in the context of directed graphs, they're called directed edges or arcs. But we'll be specifically focusing in on undirected graphs today. So anyways, when we talk about exploring a graph, what we would normally do is we would have a couple different ways we can facilitate this. So the first one is using what we call depth first search, which I'll abbreviate as DFS. Another one is what we call BFS, or breadth first search. So in depth first search, you search depth-wise into the graph. So what I do is I put my Explorer hat on and I just go, let me just get that out. There we go. So what I do is I put my Explorer hat on and imagine I'm going to go exploring in a jungle. The depth first search way of doing that is I just go straight head first into the jungle. I go, and I go run into the jungle. I go as far or as deep as possible into the jungle. When I bump into a wall and there's no other way I can go, I retrace my steps. Now, I don't just do this. Actually, I make it sound like it's really, really silly. But it's actually an ingenious idea if you bring another tool with you, a string or spool of thread or string. So what you do is, before you go running into the forest, you take it, tie it around your waist, And then what you're going to do is, if you run into the jungle, keep and make sure you tie the other end of the string to the entrance of the jungle. So whenever you run out of options, you're going to start spinning around, rolling yourself back up in that string, and winding back your way through. And before you do go back all the way, you just examine the next option or next path you can take. And then you run, and you run all the way that way. And then you wind yourself back up and so on. So this is a depth-wise exploration. And I must stress that a graph traversal is merely where we process all the edges and vertices that are reachable from a given vertex. And if ever I wanted to restart this entire process, as we're going to see today, what I can do is I could just simply take this process, start it with another vertex that isn't marked. So a mechanism when we explore these graphs are going to be edge markings. So we can mark a vertex, and we'll have it where we can add labels to edges. So we would have a vertex, we can mark it, and an edge, we would label it. And the whole idea is that in a graph traversal algorithm is that we want to process all of the edges and vertices that are reachable, meaning that exists a pathway from the starting vertex that I start off, say me starting at the entrance of the jungle, so that I can go to all the places I can reach. That means there exists a pathway to said places. So this is, so the way this gets facilitated, this ball of string that I've talked about, is actually a stack. So if you're wondering what this would look like, is that when I examine a new spot, what I'm going to do is I'm going to mark it. So I would start off by marking that vertex. And then what I would do is I would examine all of the incident edges. These are edges that are going to be off of the given vertex. Say if this was U right here, I look at all of the edges incident on that vertex. That's what we would say. So we examine each one of those, and we look at its opposite endpoint. So the edge, if I give you an edge, its endpoints are the vertices that you have on the ends. Kind of like if I pick one of these up like a dumbbell and I go like this. So the two ends of it, those are the endpoints of the edge. So what I would do is I would go through for each one of the edges. So for each edge, UV, so I go through each one of them. So this would be V, then that would be V, then this would be V. So I go through each one of them. And then I examine it if that edge isn't labeled yet. If UV is not labeled, meaning that we have not yet done anything with this edge. If that's the case. And then there's two possibilities. Either I've already been there or I have not. If I've already been there, then I would just continue and proceed, right? Actually, no. Would I? No, right? I wouldn't go revisiting places I've already been, right? So what I would do is I would simply label this as an edge that we call a back edge. What does that mean? It means that it would take me back to a place I've already been before. So if V is marked, then you would just simply label UV as a back edge. So you would label it as a back edge. Otherwise, we have discovered something we have not yet explored yet. But what does that mean? That means that we have a new edge that we have not yet examined, which is true because it's not been labeled yet. But also, it means we can continue our search. I can continue running down that way, like I'm running through the jungle with, like, I have my head cut off or something. So what I would do is I would label UV as discovery edge. So keep in mind that discovery edges are sometimes called forward edges. So I'll usually, when I talk about a discovery edge, I'll just remind you that it's a discovery or forward edge. So I must stress that we're talking about undirected graphs here. If we talk about directed graphs, there's actually a far further characterization for what kind of edges you might be running into, even for depth first search. But they're related to things we've talked about before. So once I've done this, I will then proceed to the other endpoint and continue running down that way. And that is what DFS looks like. Piece of cake, right? So just as an example of what I mean by this, so suppose that I have this graph like this. So suppose I have this graph where it's 1, 2, 3, 4, 5. And suppose that we start off at vertex 1. Start at vertex 1. So what would I do? I would mark this vertex. Now, I must stress this emphasis on the stack. So I must stress that when you start this process, you start off at U, which is vertex 1, right? So what you would do is you would naturally have it where you have a call for DFS on vertex 1. And then you would look at your incident edges. So you start off by looking at this first one. But to keep in mind, it doesn't matter which one it is. So suppose I go this way. So this would be a discovery edge. And then what I do is I apply DFS on 2. And then, but on that, I mark it. And then I look at my incident edges, right? So I start off with picking any one of the incident edges. So this one, notice it's already labeled. So I won't consider this one again. Then let's suppose we take this one. So I label this as a discovery edge. And then I go and visit 5. So that means I'm going to mark it. And then I look at my incident edges. So notice this one's already labeled. So I'm going to let's consider this one. So let's go over to 3. That means I'm going to visit 3 over here. And then let's see what we have to do here. Well, same idea before, incident edges. Notice that if I examine this one, that edge already takes me to a vertex that's been marked, right? So this gets labeled as a back edge. So I'll use dashed lines for those. And likewise, no. Look, this one's already labeled, so that means that this one here is a discovery edge, because notice its other endpoint is not marked. So we're going to go to 4. Then I'm going to mark that, and then I look at my incident edges, but notice that both of these vertices, regardless of whichever one I pick first, it doesn't matter, both of these are back edges. So then notice that I've examined all of the vertices that I could consider, all my neighbors from 4. I processed all their edges. All the incident edges have been considered, so I'm done at 4. So this is when I turn and wrap myself around the string, and I work my way backwards through the graph. So now, that means that there's no other ways I could go. And I must stress that this backtracking process where I go backwards can happen several times during the search. It's just that in this case, since the graph is nice, it has this nice property where I was able to kind of examine the whole thing in one swoop. I didn't have this issue. So notice that I go back to 3. Notice that all of these have been processed. So then I go back. Well, notice that now I'm back at 5. Notice it's always the top of the stack here. So I have 5. So I've done processing that. I go back up to 2. Notice all of my edges are labeled. And 1 is labeled. Notice I've processed the entire graph. All the vertices are marked and edges are labeled. And this is true if the graph is connected, meaning that there exists a pathway between any two vertices, then I'm able to do this and process the entire graph. If it isn't the case, as we're going to see later on in our lesson, it will be the case that we will not have it where we revisit all vertices. We may have to run DFS again on another vertex that isn't marked. Okay? So that's DFS. One thing I must note is that the running time for DFS and BFS are the same. The main conceptual difference between these two algorithms, or frameworks for algorithms, I mean itself it is an algorithm, is that this uses a stack mechanism here. So notice it's using a stack to keep track of the information that we have for exploring our graph. Breadth first search uses edges. sorry, not net edges. I'm getting ahead of myself. It uses a queue. So this is a stack-based graph traversal algorithm. This is a queue-based graph traversal algorithm. So BFS uses a breadth-wise exploration. So just to give you a contrast between the two, so in depth first search, I could run straight out into the forest, just go, woo, I just go, and I just kind of run in, but I examine everything as I'm going deeper and deeper into the graph. But the thing is, I go all the way far as possible into the graph, going one route, then I start backing up, and then I examine more routes, just like I did over here. Just by happenstance, I labeled the edges as I was doing it, just to illustrate the point of these edges. But in here, what we're going to do is, instead of it being that way, I put a pin in the ground, and I take my string, and I'm going to make it so I measure out how many steps I'm taking away from the start. So I would, instead of looking at it as, oh, I go as far in as possible, like I did here, like where I go, ah! Instead, I go level by level, or layer by layer, through the graph. So instead of taking and just running right into the jungle, instead I take 1 step into the jungle, 2 steps into the jungle, 3 steps in the jungle. These steps correspond to the number of edges you use to explore into the graph. And in this case, it's very similar to this. In contrast, however, we have to have it where we have to be a bit more careful. We can't just simply just... and I must stress that the reason why I represent it like this, just to show you that you can represent it nicely using recursion. But if you don't like it like this, you can represent instead it using your own stack. Just you have to be a bit more, you have to be a little careful when you're doing this. So, anyways, let me tell you what BFS looks like. And I must stress we're going to see both of these again and again today. So I must stress that it won't be just simply be like, oh yeah, this is the first time you're going to see it. We're never going to talk about it again. You'll get to see it again. So if you're copping in later on, don't worry, it will get readdressed. So as I'm going to have a queue, I'm going to start off by initializing a queue. So I'm going to start off with a queue that's empty. And what I'm going to do is imagine I have some starting vertex. So suppose that I use the same graph here. Actually, let me just draw it again over here. 1, 2, 3, 4, 5. And I must stress the reason why I'm doodling this a little small is because we've talked quite extensively about this the other week. Okay. So suppose that this is U here. And I must stress it doesn't matter which graph it is. It's just, this will cut it. So I start off with an empty queue. What I would first do is I'm going to do the following. So what I'm going to do is before I do anything with this queue, I need to take into consideration what it should look like, okay? Sorry, I'm just taking a quick peek at one small detail here. So what I'm going to do is I'm going to put into the queue U. So I'm going to NQ U, so it's in the queue. So I'm going to draw a queue like this. Imagine just like you're sitting in line, where this is the front of the line, that's the back of the line. That's what a queue is. And we can NQ or enter objects into the queue, and then we can DQ or make them leave, right? Same idea. So once we're done with them, we can DQ them. And that's the whole point, is that when the vertex reaches the front of the queue, we can process that vertex's incident edges. That's why we're going to use it. But the thing is, I also need to mark U because I'm going to place it into the queue. Now, this is going to be a little bit different than here, where I mark as I go. As soon as I visit a vertex, I mark it, right? It's going to go into the queue when I mark it. Now, you might say, Dan, why is that the case? It's because we don't want to reprocess a vertex as we take it in once, the very first occurrence for which we've encountered that vertex. We don't want to re-examine it. Why? Because we're going to go breadthwise through the graph. The very first time I run into it, it better be using a least number of edges. So, for example, if I were to start this off, I would put 1 in here. And now I mark it. because it went into the queue. It's not when that way I know for sure one is never going to go back into this queue. Now, what we do is we check while the queue is not empty. So we're just going to keep doing this until we've processed as many, all the vertices that are reachable from the starting vertex. Means that there exists a path. So while the queue is not empty, what we're going to do now is we're going to take our vertex out of the queue. So I'm going to call that V. So I'm going to dequeue it. We dequeue it from the queue. So for example, I take one out, I hand it over to my favorite friend, the goblin, and he goes, "Hey, it's my precious." That's what the goblin would do. So the goblin now has our vertex, and now we're going to take this vertex away from the goblin, and then we're going to say, hey, look, let's look at all of our incident edges and see which way we can run, okay? But the thing is, we're only going to run one edge away. Why? Because we need to make sure we don't run into a dead end, because the goblin's going to come get us, okay? So we want to be careful. So what I would do is after this, I go through for each edge VW. So I'm going to look at the incident edges on that. So I look at each incident edge. So I'm going to have the opposing endpoint W. So for example here, what I'm going to do is I'm going to consider this edge and this edge. I must stress that it's not going to be like in DFS where we kind of just run right in. We're going to examine these first. So like I said, it's going to go level by level through. Like if I'm taking a pin and I measure out string, how far away I'm going from my source. So watch this. So now I'm going to just check if the edge is labeled. So VW is not labeled. Then we check if the opposing endpoint's marked. If W is marked, let me just get my eraser here. Is marked, getting a little ahead of myself. If W is marked, then that means that we don't have anything to explore there, right? It just means we're going to label an edge. Then what we do is we label VW as cross edge. So in BFS, we have these things called cross edges for an undirected graph. So just be mindful that they have a somewhat different purpose than they have for the back edges, but for a lot of applications, they're no different. I must stress that it depends heavily on the fact that it's an undirected graph. Otherwise, we have a discovery or forward edge, right? So otherwise we label VW as discovery edge. As discovery edge. And then what we do is we're going to put W into the queue. But we want to make sure we mark it as well. So we're going to mark W, and then we're going to enqueue it in. So we're going to go q.enqueue. We're going to enqueue it into the queue. And there you go. So one thing I must stress is that we can build a tree, as we're going to mention in a little bit, by simply modifying this ever so slightly. But let me walk through an example now. So I've just taken one out of the queue. So let's see. So I got to go through all my incident edges. So if this is not labeled, then what I'm going to do is I'm going to have a discovery edge, right? Then I'm going to enqueue. I'm going to mark 2. Then I'm going to place it in this queue. And then I go through my next incident edge on 1. I have a discovery edge. I'm going to now notice that this is not marked. So it means we're going to mark it. We're going to place it into the queue. And now I've considered all my incident edges, right? So now I'm done with 1. Now the goblin grabs 2. And now let's consider all my incident edges. Well, this one's already been processed, right? So next we have this one. Notice that its opposing endpoint is not marked. That means we have a discovery edge. It means I'm going to put mark 5, and we're going to put 5 into the queue. And then lastly, of course, we're going to consider this incident edge as a discovery edge. I'm going to mark 4, put 4 into the queue. And then I am done with 2. So then 2 is gone. Now the goblin grabs out 3. So 3 is now what I'm hanging on to. I go through my incident edges. This one's is already labeled. This one, however, is not. Notice it is a cross edge. I do nothing with that after. And this one's also a cross edge because its opposing endpoint is also labeled. Sorry, its opposing endpoint is marked. And now we're done with 3. Next we take 5. So the goblin takes 5. Now we gotta run away from 5. So now let's take a look here. So that's already labeled. That's labeled. This one is not labeled, but however, its opposing endpoint is marked, so it is a cross edge. And lastly, we take out 4. The goblin's got 4. We better take it and run with it, okay? Let's see which way we can go. Well, this one's labeled, that's labeled, this labeled. We're done with 4. The queue is now empty, so we've performed what we call a breadth first search traversal. Just like over here, we did a depth first search traversal. So you might say, Dan, why is this so, why do these two exist? It's because breadth first search has its own properties. DFS has properties too. DFS is nice and simple. However, one thing I must stress is that you always would, depending on what your graph looks like and how breadth-wise or how bushy your graph might be, you might consider one or over the other in practice. But I must stress that their worst-case time complexities are the exact same, depending on how you represent the graph. So, for example, if you have what we call an adjacency matrix to represent the graph, both of these will take big theta of n squared or big O of n squared time, both of these, and the adjacency list representation, they'll take big theta of n plus m. Now, I must stress that depending on what your graph looks like, these might get specialized even further. For example, we talked about the idea of sparsity, where there's not many edges. In that case, you can actually have it where if a graph has, say, a linear number of edges with respect to the number of vertices, this would be devolving down to something a little bit better. So instead of this being n plus m, it'll just be n. Which does occur for certain kinds of graphs, such as trees, and also I mentioned about so-called planar graphs. There's a lot of graph classes that are like these out there in the wild. But yeah, this is DFS, that's BFS. One other property I wanted to point out to you, and we talked about this briefly last time, was that if you look at the discovery edges, or forward edges, they always form a tree. Now, the first thing we're going to do when we talk about our lesson here today, we're actually going to prove that. So I just asserted that that was the case. However, that may not actually, we have to make sure that that is in fact true. We can't just pontificate about it. We actually have to check that. So we're going to actually prove that here today. So that's true for DFS and BFS, that the discovery edges form a tree. So if I take the edges that form all those discovery edges, that subgraph, when I put that together, is in fact going to be a tree. And especially if it's connected, it's what we call a spanning tree. If it is not connected, it is a spanning forest. And each one of these actually has their own properties. So specifically, BFS has a nice property where this tree that you get as a result of this process is what we call a shortest path tree. Meaning that, and this is because every time I take in 1 step, 2 steps, 3 steps, I increasingly visit each vertex based on the number of edges I use. Meaning that when I'm done this process, I actually have it where I have a shortest pathway from each vertex from my starting or source vertex, which is a really nice property. So if you ever find yourself needing shortest paths in an unweighted or undirected graph like this, you can use BFS just like this. And I'll show you how you can actually compute that path today in a nice simple way using this tree. So one thing I want to acknowledge is that that once you have the tree, you might ask, okay, Dan, how do you know what the tree looks like? So something you just simply modify in this algorithm is that you would add in two little parts here. You would assign the parent of the starting vertex to be null or nil, whatever you would like to call it. And down here, whenever you put in a vertex into here, you're just going to put in the vertex for which you got to W. So you would have W.parent is assigned V. That's the vertex you used to get there. And if you notice this, if I say pick off any vertex after this, and I ask what its parent is, it will lead me back to you at the beginning. So we'll talk about that today, okay? So this is all the preamble you're going to need for talking about stuff we're going to do today. So hopefully that is clear, everybody. Let me know in the chat if you're hanging on out in the chat. Let me know if this helps you out a little bit. Let me just erase this, then we're going to get started, okay, everybody? I'm really excited. Okay. Okie dokie. We've got ourselves. So anyways, let's get into the lesson here for today. So let's get this. I'm really excited here. Okay, everybody. So today we're going to be talking about properties and applications of graph traversal algorithms. By no means will this specifically be a complete list, but this will give you a flavor for some things we've talked about either previously, or it'll be things that'll help supplement some of the discussion we've had previously. So the first thing I would like to do is talk about a property that I sort of just said it previously, but I didn't actually prove it for you. So I want to remind you of something that we talked about involving depth first search traversals and breadth first search traversals. So the first thing is that suppose I give you a graph, say something that looks like, so yeah, I'm going to number these 3, 4, and 5. So suppose I give you this graph. Now, if I were to perform a depth first search traversal on this graph, so remember the process. So suppose that this is the starting vertex. So first I would mark it, and then I look at my incident edges. So I try to run down as far deeply as possible, and whenever I have more options, I wind back, like my ball of string, like we talked about in our story of Theseus and the Minotaur. So in this case, suppose I consider this incident edge. So remember, we labeled these edges, right? We had what we called forward or discovery edges, which I'm going to label here in blue. So suppose I go this way. And then I'm going to mark this vertex. And then I consider my incident edges from here. Notice that I can go this way. And then I'm going to mark this vertex. I'm going to consider my incident edges. Suppose I go, let's go this way. And then I would mark this vertex. I consider my incident edges. So notice here that the opposing endpoint of this is already marked. So that means that I have a back edge. So I'm not going to go down this way. That makes no sense if I'm trying to process this graph, right? Because I've already been there. I'll be back there eventually. then I notice this one here. Well, this one I have not gone down yet. And let's mark that vertex. And now let's process my incident edges from here. So notice that this edge here, so keep in mind, it doesn't matter which order you consider them in. This one already has the opposing endpoint marked, so this is a back edge. This one's already marked, so I got a back edge here too. And notice all my edges, incident edges have been processed. So now I'm going to wind back up my string, which, remember, what kind of data structure is this underlying representing? A stack, right? So I go back down to 3. Notice that all my incident edges have now been considered. Notice, same thing here. When I reach these ones, they all will be labeled, right? So I could go back this way. The same idea, same idea. Notice that all of the edges and vertices are processed. However, notice something. We said something actually last time, was that these blue edges, the forward or discovery edges, they always form what we called a tree, right? Remember, a tree is an acyclic graph that is connected, right? But furthermore, it isn't just that. If the original graph is connected, it is what we call a spanning tree. So it means it contains all of the vertices of the graph. Now, if the original graph is not connected, then we would call this a spanning forest. So we'd call it a spanning forest. So if you were to, for example, use DFS on the entire graph, and say you had to rerun DFS on a given vertex more than once, so if it's unmarked, so say you run it on 2 unmarked vertices, you know you're going to have 2 connected components, which we'll talk about at some point here. But the point is that it'll contain all the vertices of some connected component. So this is just an assertion, right? I just asserted to you that it takes this form. This is something I've said previously. However, and I must stress that this is also true for breadth first search as well. You can use the same process there as here, with the exception now you're going breadth-wise, so the underlying data structure is it a stack? No, it's a queue, right? So I actually have to prove this for you, that it actually, the discovery or forward edges form a tree. So in particular, it will be the case that it contains no cycles, right? So that's what I want to prove for you, is that it's going to contain no cycles. Because any of these would not contain any cycles. So let's prove this here together. So enough of me just asserting that. Let's actually prove it. So here's a theorem. So theorem. And I assure you that the argument I'm going to present here, it will work regardless of which kind of traversal it is of these two. So DFS or BFS. Furthermore, it will also be the case that this will be what you need to prove a claim like this. So the argument is rather cute. So consider the subgraph T formed by discovery edges, discovery or forward edges, whichever terminology you'd like, via a DFS traversal, or a BFS traversal. So the claim is as follows, that T does not contain any cycles. It's acyclic. So T does not contain any cycles. So you might ask, Dan, how the heck are we going to prove that? Now, we're going to pull up one of my best friends, proof via contradiction. So let me give you the game plan for how this is going to play out. So what we're going to do is we're going to assume that T, remember, in the claim, the blue edge is that's what t is in this one specific example. So I must stress that we don't necessarily know this. We're trying to prove this. So here's the game plan. What we're going to do is we're going to assume that actually it's possible for t to contain a cycle. So once we have that, we're going to see, based on either one of these two algorithms, and I must stress the way we're going to formulate the argument, we're going to try to pick something that both algorithms do. Now, if you're not convinced by the argument I give you just for both of them in the simple way I do it, I encourage you to pick up each one of the graph traversal algorithms and examine it carefully to see that this is indeed the case. So what we're going to do is we're going to see what happens with these two algorithms. We're going to see if the assumption that we make, our presumption, leads us to what we call a contradictory statement, a statement that is always false. So one that's very common of this form is something like if I gave you a statement and say A and not A. You can't have both of these things like that. That statement is never true because it's that A and not A at the same time. And so if you made it that A is true, then not A is false, right? And if A is false, then not A is true. And that means that regardless of which scenario you give me, it's always going to be that it's just a bunch of hooey, right? So here we go. So I'm going to construct an observation in a moment. So let's see what happens carefully. So assume otherwise. So assume otherwise. Then T contains at least one cycle. And I'm going to give this cycle a name. I'll call it C. Now, what kind of edges is the cycle comprised of? It's comprised of forward or discovery edges, right? The same thing, right? That's what it has to be because it's a part of T. A cycle of discovery edges from a DFS or BFS traversal. Right? Now, let's take a very careful look at what this would look like. So we're just going to pretend. Now remember, if our statement is actually not even true, like if this theorem was false, I should be able to present such a graph to you. So there is a cycle somewhere. However, we're going to go along with the presumption here and suppose that there exists a cycle. Now, do you remember our example here, like when we process this graph? Now remember, the statement has to be true regardless of what the graph looks like. It has to be any undirected graph. So suppose that I have it where, say, when we considered, say, vertex 5, suppose that when we reach vertex 5, we had it where a cycle got formed. Like suppose that there's a cycle like right here. Say this is a blue edge, for example, instead of a red one. Now suppose that we put that there, and all of the other incident edges, so other edges that form the cycle, already are processed. Well, there's something that we can say about this edge. It's a very special edge. So let me describe this edge to you. So consider the last undirected edge E UV. I'm going to use rounded parentheses just to indicate like which order I discovered them in, but I would normally use curly braces here. Consider the last undirected edge E added to C. So for example, in this case, the cycle would comprise this triangle here. So suppose that's the last edge that gets put in, that forms that cycle. added to C in T, where, suppose that this is the vertex I reach before to add that edge in. Suppose that's U. Where U, sorry, we'll say where at least U was marked first. Because to add this edge to the cycle, which would be corresponding to labeling it as a discovery edge, I had to get there somehow, right? So that's what U is. Now, the thing is, to get to U, I had to mark it, regardless of which algorithm you use. So in one scenario, if this is DFS, that means that I reached here, and then I mark it first, then I consider my incident edges, right? In BFS, the way it works is that I would have placed U into the queue, and it finally got its turn, but it would have been marked. So now, as V is an endpoint, of some other edge in C, V is marked, right? So for example here, just to illustrate what I'm talking about, this would be V right here. But remember, V is already marked, because remember, this is the last edge I add to the cycle. That means that there's at least one other edge out there that has and comprises the cycle. Meaning that there was some other point previously in the algorithm's execution that had to have marked the other endpoint. Do you see where we're going here? Because if you remember the algorithms for DFS and BFS, you would know exactly where we're going with this. So watch this carefully. So now we know that V is in fact marked. By observing this, one, by observing this, instead of saying by observing this, let's say as a consequence. I think that's a much better way of putting this. I always like to encourage you to find ways to lay out your argument carefully. As a consequence, both endpoints of E are marked. But what does that mean then in either algorithm? Is it a discovery or forward edge? Let me walk you through. Remember, suppose that we were at this vertex at that time and we added this, supposing under our assumption that this is in fact a discovery edge. However, we've observed that also this endpoint is also marked. In either algorithm, this would not have been labeled a discovery edge, right? It would have been labeled as a back edge or a cross edge. Of E are marked, implying E is a back, say if we're talking about DFS, or a cross edge if we're talking about BFS, not a discovery edge. Therefore, now, you have to always be careful when you make arguments like this, right? You have to remember back to the algorithms we presented. They will process every one of the edges and vertices in the graph, presuming it's connected. Likewise, we only label edges with two different types. Forward, or discovery edges, and back edges if we're talking about DFS. In BFS, we label discovery / forward edges, and cross edges, right? So notice there's no other options. So that's a very important thing, and it's so important I'm going to put it down here, because I must stress that depending on what kind of graph you're playing around with, like right now we're talking about undirected graphs. If we're talking about a different kind of graph, we would need a stronger statement here. Therefore, as the graph traversal labels all edges and are only discovery edges. I'm just going to abbreviate discovery with disc. Discovery edges or / cross edges, depending on which algorithm you're talking about, or / cross edges. Cross edges. What does that mean? What does it mean? We've assumed that we have a cycle, right? We've assumed there is a cycle. That means that this edge E exists, right? That edge E exists in this subgraph T, right? Now we've waded through the jungle carefully, and we've come to also the conclusion, as from that presumption, that also edge E isn't in T, right? That's what it means, because it is not a discovery edge. So both, it is the case that both E is in T and E is not in T, which this belies our assumption over here. And that means that we have a contradiction. So you can't have both of these things at the exact same time. And that concludes our proof. So a contradiction right here. So we've yielded a contradiction that assures us there are no cycles. Because if there was, I could show you that there is actually, by the way the algorithm constructs T, it is actually going to be the case that whatever that edge would be, like the one that we have, that we would observe to exist, because it actually will exist always, because at some point you have to form the cycle, right? If you have this in place, which is the presumption you get when you assume there is a cycle, then it has to be that that edge also doesn't exist at the exact same time, which is impossible, right? So interesting stuff. So that is how we can know that whenever we do a DFS traversal or a BFS traversal, we can ensure that if we look at the discovery edges, whether you want to collect them up in some data structure, or you would like to, say, for example, associate parent references. Say each one of the vertices has a parent. You can ensure that this will always take the form of a tree. There'll be no cycles. So in fact, that is specifically if it is connected. If it is not connected, as I said already, it is a forest, but it's even better than that. It is a spanning forest. Every vertex will be included in this forest, which is lovely if ever you need to, say, compute a pathway. So let me just move on over here. Are there any questions or anything? Don't be shy. Don't be shy. I'm rather happy to answer any questions. So yeah, so this is one way you can prove that whenever you're done BFS or DFS, you're going to end up with a tree for those discovery edges. So a tree-like form or a forest. So if you're running it just once, you'll end up with a tree. And it will be a spanning tree if it is connected. Otherwise, you're going to end up with a spanning forest. Pretty interesting stuff, right? I think that argument's really cute. Because all it is just that we presume that there's a cycle, and then we observe that the cycle has to take a certain form because of the way the algorithm works. So that's the key observation, was that we knew that that edge E exists. If it exists, then we can see what it means when we actually just plop her right in, okay? Okay, so if there aren't any questions, let's proceed to my next thing I would like to talk about. So let's get on that. Okay, so in an earlier lesson, we learned about how we could compute paths using depth-first search. I want to show you a broader, arguably simpler or reusable way you could compute paths from a given start vertex to any other vertex that is a part of the graph should it exist. So earlier on in the lessons, we talked about how when we run DFS or BFS, we end up with a spanning forest, and specifically if the graph is connected, we end up with a spanning tree. This is something that we've proven together. So you might ask, Dan, how can I use this information to compute a path? So when you execute BFS, for example, as we've seen previously, you can associate a parent attribute with each one of, parent or predecessor attribute with each one of your vertices. You can have a parent attribute for each one of them. So I can have a parent for each one of these. Namely, the root of the BFS tree or DFS tree will have it, that's the only one, because it is a root, will have no parent. However, each successive one will have whatever node it took to reach that one at its first occurrence would be its parent. So in this case, the parent of 1 is 2 because this is where we'd started off originally our tree traversal. Sorry, not our graph traversal. Sorry, I get very ahead of myself. So naturally, the parent of 4 would be 1, the parent of 3 would be 4, and the parent of 5 would be 3. Just follow along the discovery edges, because remember, the discovery edges form our spanning forest. So in this case, it's just a spanning tree. Now, do you see how I can use the information I have available to me to compute a pathway given two vertices? So for example, if I start off at vertex 3, notice that I have the parent for which they'll take me from 3 to 4, and this will take me from 4 to 1. This will take me from 1 to 2, because its parent is 2. I could trace myself all the way back to 2, say if I wanted to find the path from 2 to 3. So if I know a given vertex that I'm going to go frequently computing paths from it, say a given source, what we would call in the pathfinding terminology, the starting vertex or source vertex, say we have several times we would like to recompute that information. If we compute the DFS tree or BFS tree, we can keep these parent attributes around. If we have access to that given vertex, then I can trace through the parents to get back to the other endpoint of the path, or the other end of the path, to be a bit more precise. So let's talk about this. So previously I showed you how you can compute a pathway in a graph using DFS. We used a stack that we would hang around with, say that was accessible to our algorithm, or think of it as a global variable if that makes it easier. And we would store in the pathway, we'd use a stack to store that information so that if we pop off the stack, we get the pathway in reverse. Now, what we can do once we have this tree and we have access to both of the ends of the path, the desired one, if should it exist, we can say hang on to that information in a very similar way, except we don't need a stack to do it. We could just simply use a list because we have all the information to get from point A to point B. We don't need to have any other mechanism to help us along with this process. We've already computed that information. So suppose there is a list, which I'm going to call P, mean path. To store the path. And we're going to try finding pathways using the DFS tree or a BFS tree. You're going to see it's actually much simpler once you have this tree at your disposal. Like, much simpler. And it's very easy to augment with different data structures should you would like to use. Instead of a list, say something else. So, one thing I also want to point out to you is, say, for example, let's take our previous example. Suppose that I was using a list to store the vertices of each one of the ones in the path. Suppose I'm trying to find a path from 2 to 3. So suppose I want to get a 2-3 path. Or if you think of this as U and this is V, I want a UV path. Which we've defined previously before, the idea we have two endpoints, the two ends of the path. So in this case, what I could do is I could store in my list. I could just imagine I have my list here. So I start off with an empty list. And you imagine at the end of this process, I would like P to be empty if there does not exist a path. But if it does exist, I would like it to store the vertices, or if, say, if I wanted to augment this, say if I have the edge of the list of edges, I could do that too if I would like that. I can have another list that does that. What I could do is I start off at V, so I just put 3 in there, and then I would follow my parent. And look, there's 1 for the parent of 4, but notice that I'm at 4, but 4 isn't like the furthest up in my tree, right? I haven't yet got the root yet. So I could just insert this at the front of my list, and then I can follow my parent. I go to 1, I can insert that at the front of the list, and then I could follow my parent. It takes me 2. I put 2 at the front of my list, and notice my parent is null. Notice that I have no other elements to consider at this stage. But notice now that I have, in fact, a 2-3 path. Notice that it's UV path, 2, 1, 4, 3, 2, 1, 4, 3. The thing is, so I always insert at the front of the list. I can ensure that they're actually in the order from U to V in terms of the pathway. This is in contrast to the stack, which would give it to you in reverse. But it will be correct. It will just be in reverse. So you'd have to just fix it by just popping them out and then just put them into the list in a manner that's quite similar to this. So now let's see how this would work. Now you might ask, Dan, what exactly do you do here? Now, because I didn't show you this specifically for BFS, like the BFS tree, I'm going to show that to you, seeing as I used in my example the DFS tree. So let me show you what the algorithm would look like if I was doing this with the BFS tree, but I must stress that it doesn't matter if it's the BFS tree or a DFS tree. I just wanted to pick one of them for you because in our notes, I have it where it shows you the explicit lines in pseudocode for building this tree. So we're going to call the algorithm. So algorithm is going to be called find BFS path. BFS path, breadth first search. We're not doing anything with binary search trees today. So it's input. We have the vertices U, V, which are in the set of vertices of some graph G is equal to V. Now, the big assumption here is that the BFS tree already exists. That's a very important element of this whole thing. It's that whatever tree that you're going to use, the DFS tree or the BFS tree, it has to exist already for this to work. So that's an important assumption. So this is an assumption that I'm going to make. So this would be a pre-computation. Assumption. We have the BFS tree. So we already have this. Welcome on in. Welcome on in. So now we have our vertices. And what we're going to do is we're going to have it so it returns true if the UV path exists, and false if it doesn't. And I'm going to stress that this list P is going to store the pathway in terms of vertices. So true if we have a UV path that exists, and is false otherwise. So watch this. This is going to be much simpler as an algorithm, at least, because we already have all the information constructed for our tree. Now, I must stress that this is not a BFS tree over here. That's a DFS tree. However, the same principle applies. So this algorithm I'm going to present to you, it doesn't matter if it's a DFS tree or a BFS tree. It's just that, like I said previously, the notes already show you how to build the BFS tree. So I'm just sticking with that. So all we're going to do is we're going to have a reference to the one end of the path, namely V, and we're going to trace back over to U by following the parents. So wow. And when did we stop doing this, right? We stopped doing it when we hit null, right? That's when the parent was null. So we're just going to traverse along. We're going to go around on that pathway. But remember, the principle still applies, no different, whichever tree it is. As long as it's set up like this, where we have parent attributes or predecessors. So while this is the case, what we're going to do is we're going to insert at the front of our list. We're going to insert our current vertex. So this will place it at the front of the list, akin to our example. And then all we're going to do is we're going to update cur_node to be the parent of cur_node. So it's going to just feel like you're just doing a very simple traversal, okay? It's a piece of cake. You're just going to work your way back around like this. But the thing is, we're just going to always place it at the front of the list. That's why it keeps it in the correct order. If we put it at the rear, it's going to end up backwards, like on our example we did previously, where we used the stack. We were just doing cold turkey searching for a path. Now, once I have this information in my pathway, how do we determine if we found the UV path? How do we know if we found it or not? That's the big kicker. So and I must stress again, I must reiterate this because I know somebody will take a look at this and be like, Dan, that isn't a BFS tree over there. It doesn't matter. That's the point. So suppose that I were to get a path from 2 to 3. So I would start off at 3. I work my way back over here to 2. I finish when I update cur_node to be null. So that means that that's where I'm at, and this is actually what would be in P, our list P. I'd love to call it list L. Seems right natural, but it's a path. So this would be what's in that list in this order. How do I know I have a UV path then? How do I know? Well, surely U has to be somewhere in this list, right? But it's not just anywhere in the list. We could be much smarter than just that. Well, certainly, is U going to be at the back of this thing? Somewhere in the middle or at the front? Well, it's always going to be at the front of the list. Because every time we insert, we always do it at the front of the list. So it means all I have to do is just look at my list, look at list P, see if U is the very first element in P. That's all I have to do. And you can do that in constant time. If U is at the front of P, then, if that's the case, then you're just going to return true. Because that means you have a UV path. And in particular, P will store that information. So that means that if you go accessing P, it will have the path. Otherwise, we have to do some cleanup. Because remember, it may be the case that we start off V somewhere and then it just dies somewhere. It just keeps following its parents and then it just gets killed somewhere along the lines. It just couldn't reach U because U was not at the front of P. So it means that we need to clear out that list. So I must stress that this is only if you want to make sure, like keep in mind, if you're using this, if this returned true, that's how you know there's a path. If it isn't, then you could just clear out P and not use it, right? However, I'm just going to put just for as a safeguard here, because if we're trying to be considerate to those that aren't going to do this, I'm going to empty list P. So that means that no path exists, no UV path exists. So you empty the list. So it means that you're going to potentially have to get rid of a whole bunch of vertices from this. So you're going to have to go through each one of these, get rid of those. So just remove them. And then you just return false, meaning that we failed to find the pathway. Now you might say, Dan, why would you show this only, because your example uses a DFS tree. Why mention it in terms of BFS? Well, one, like I said, I already showed you how to do this with DFS, but likewise, I wanted to show you specifically with the BFS tree because as a reminder of something I've said in a previous lesson, this will actually, if you were to compute the BFS tree, which is, it won't look like this, what will happen is you'll end up with a shortest path tree. So it means that if you start off with some vertex U, like say you have this one here, and suppose that you did compute the BFS tree of this, you can keep reusing that BFS tree to compute shortest pathways from a given vertex to your starting one, your source vertex. So you keep using it over and over and over again. So this means that you can, if you have a BFS tree, you end up with paths that have a least number of edges between those two endpoints or ends of the path. Furthermore, it also lets you reuse it. So the one benefit of doing it where you compute the tree, as opposed to doing it from scratch every single time, is that if you're going to be recomputing pathways from U to some other vertex, you could keep reusing this tree over and over again. It'll save you time. So pretty fascinating stuff, right? So let me get the chat open here. So keep in mind, for those that are watching, I do have an earpiece so I can hear things that are happening, whether it be the chat, and I also have a monitor here. So if you have questions while we're doing stuff, please don't hesitate. Or if you find yourself wanting to say some funny stuff, go for it, please. We're having ourselves a blast here. But yeah, no, please, everybody's having a beautiful day so far. But yeah, no, so far we have proven that if you give me a depth first search traversal or a breadth first search traversal, that the resulting tree or the resulting subgraph will be a spanning forest. It will not contain any cycles in it. So we proved that. And also I've shown you how a simpler way of getting a reusable pathfinding algorithm. So the whole idea is that if you find yourself computing this tree, you can keep reusing it. The one drawback I will stress is if you're finding yourself pathways from other vertices, other than you, there may not necessarily be the case that you're going to end up with the one that you're looking for. So just be mindful of the fact that this is the shortest path tree. It consists of shortest paths. But if you find yourself needing to recompute it, you may have to do that if you end up with a pathway that you're not ideally looking for. Because remember, this is the shortest path tree from you to every other vertex. It may be the case that it might differ for other vertices. I mostly mention this because there's some other algorithms out there when you consider what we call weighted graphs, so ones with distances. You can use the same principle there. Say, for example, if you've ever heard of Dijkstra's algorithm or Bellman-Ford, you can use the exact same concept, except you'd use those algorithms instead. And you can just pick up this algorithm and you can use it. Pretty nifty, right? So to give you a little bit of a flavor for what we're going to be in for today, so that was like kind of like the first part of the lesson. So the next things we're going to be doing is we're going to talk about how we can use graph traversals to count reachable vertices or edges. So say I want to know how many vertices, because remember in a graph, this can represent all sorts of different things. This could be, for example, a social network. I would like to know, for example, how many friends I have in my neighborhood, for example. Or, for example, I may want to know all other queries. For example, I want to know how many friends I have in my social network. Or say if I want to know how many relationships exist in my social network. These are two questions you can address with the next stuff we're going to talk about here, which is pretty nifty. Once we're done doing that, we're going to see how we can test if a graph is connected or not, which is going to be an application of some things we talked about in a previous session, but that's okay. I'll start with it all from scratch. And we'll talk about how we can compute connected components. So those are going to be the main things we're going to see here today. But I must stress that we're going to be seeing more things we could do with graphs in the future. So hopefully that gets you excited. I know it gets me excited. Oh man, this is my exploring hat. Oh. But yeah, no, so let's see here. So what we're going to do next is I'm going to erase this board, and then we're going to talk about how we can use, for example, DFS to count vertices, and then we're going to see how we can count edges using breadth first search. And I must stress that it doesn't matter that I'm just only using DFS for one and BFS for the other. You can still adapt either one to do this task. It's just that I like to show you a variety, okay? That's really it. So let me just erase this, then we're going to add ourselves into the fun of all this. So of course, if you're enjoying this, please don't be shy. Make sure you tell your friends to come on out. And of course, if you're enjoying this, ask questions, leave fun comments. I mean, like straight up, whatever you feel like. It's a good time. Just keep it decent, okay? Okay.
Hi, Paige. Hey, guys.
Hello, hello. Now, I hope you're having a beautiful day there today. We're going to be talking about counting vertices and edges in a network, which is going to be pretty fun. So let's get in it on everybody. So for those that are hopping on in, just keep in mind that all that's going to happen is that even though the chat isn't visible or the text-to-speech won't be audible, I will be still hearing it, and I have all of the chat over just right here. So if you wonder why my eyes may gander over this way, that's you guys, okay? So just keep in mind that. So please just have yourself a blast. If you have questions or anything like that, don't hesitate to reach out. If you have anything funny that you want to chat about, please do so. Any small questions, I'll address them on the fly.
Audible to me, BTW.
Yeah, it's audible right now, but the minute that I go and put the chat away off the screen like this, like that, what'll happen is it will actually be not audible on the stream. So I just like to mention that because I've had it a couple times during stream where people are like, well, now I can't hear it. So yeah, that's why I mentioned that. So I must stress that I'll still hear it even if you type it. That's all I'm saying. So let's get in on this. So let's talk about another application of graph traversal algorithms. Next, we're going to talk about counting reachable vertices. Counting reachable vertices and edges. Now, you might ask, Dan, how the heck can you do that? Now, obviously, if you want to know how many vertices and edges you have, you can always keep track of that information. You can store it like an attribute if you'd like. However, suppose that I give you a big complex network or graph, and I want to know, say, how many friends do I have in my cluster, or say, our connected component, to be a bit more precise. So you can think of this like a social network, for example. You have all your friends in your social network, and I want to know how many friends do I have, and I don't have this pre-computed somewhere else. Likewise, I want to know how many connections exist between my friends in, say, a social network. We're going to talk about how we can compute that information. So we're going to presume this graph exists, and I'm going to show you how you can explore the graph to compute this information based on what we call depth first search and breadth first search. So I'll be showing you both of these in those contexts. So the big thing I really want you to observe about either one of these algorithms is that it doesn't matter which of the two. Either one will mark each one of the vertices / nodes at most once. So if we use that, we can use that information to count the vertices, presuming, because if we never attribute or count an unmarked vertex twice, we can ensure we're not going to be inaccurate with our count, as long as we explore everything that we can reach. So I'm just going to mention that notice that we visit each vertex once. And that happens when we mark the vertex, right? So this specifically happens when we do DFS. It's like when we mark it, we immediately start exploring from there. But in BFS, we would put it into a queue, and it would get its turn eventually. But that's the first time we visit it. So now that we have that information at our disposal, we can try to take depth first search, and we can always simplify it a little bit. Because notice that we never actually have to really, if we're counting, like say if I give you this graph here. Say I give you one that looks just like this. Say this is my network of friends, okay? It's not very big. Although I'm always looking for more friends. So suppose that I wanted to count how many vertices are in this network or graph. So notice that I have 1, 2, 3, 4, 5, 6. And suppose that I would like to do this. Now, if I use depth first search, the way that I would do this is I would start off with some vertex. I'd mark it. And then I would consider my neighboring or incident edges here. So the incident edges here. So these are the edges that come out of that vertex. I consider each one of them. Whichever one will take me a little bit further, I continue my search that way. So it's like if I was to just decide to wrap some string around myself and go run through the jungle and go, just run through the jungle. So the point is that suppose I consider this one. Now, I'm not going to label any of the edges like I've done previously, just to illustrate a point. So if I do this, I can visit this one, and then I consider my incident edges, and I don't know, I could pick any one. I could go this one right here if I want. I can notice that I would never go visiting somewhere I've already marked, right? But I could keep a running total or tally of how many I have. Like say I call it count, and so far it's 3, right? So suppose I were to take this route. Say I go to this incident edge. I would update this to 4, right? Because that's how many I'm going to mark. Then I consider my incident edges. Notice I wouldn't explore here, I wouldn't explore there, and I wouldn't explore there. I should mention when I go running into the jungle, I take a big stick of chalk and I put big X's all over wherever I've been. So I don't go down that way again. But the thing is, when I'm done examining where I am, I would walk backwards. I would spin myself around, raveling up that string to walk myself back, okay? So then I would go back this way, and then I would examine my other incident edges. Suppose that these ones are already examined, so I would go here. So now I would have 5. Notice I've considered all my edges. I would go back, I would ravel myself back up, go back over here. I would consider this one right here. Marked it, so I increment my counter. I consider all my incident edges, so I'm going to ravel myself up back over here. Then I'm going to ravel myself back up. And I would keep doing this until I get all the way back. All the way back. And notice that I'll end up with a count, and it doesn't matter if I label the edges or not, which is something that DFS cold turkey would do. So let me show you how this would look by simplifying depth first search. So here's the algorithm. So I'm going to call it count vert for counting vertices or nodes. So I have that as input. I'm going to take in a vertex u of the set of vertices of some graph g is equal to v. So I have my set of vertices, my set of edges. And as output, it's going to tell me the number of vertices reachable from u. So again, like I said, it's just like if I wanted to count up all the friends in my social network. Now, I must stress that the reason why I'm saying that as opposed to other people's social networks, it would be that there would be another what we'd call connected component, another potential forest if we were to look at the discovery edges. And well, another tree in a forest, sorry. So I'm getting a little excited here. This always gets me excited. So it would be the number of vertices reachable from u. So what is the first thing I told you we were going to do? We're going to mark the vertex, right? So we mark the vertex. I mark it. That's the first thing I do. I just put an X on it. I put that on there. And then I'm going to have a counter. Now you might ask, Dan, am I going to have like a variable that is, say, static, for example, for those that are programmers out there, that would keep up the counter? Now you could do something like that. However, what I would like to do is I'm just going to have it so it's going to recursively keep the track of how many there are. So I'm going to presume from my current point that I've counted myself. And then as I go exploring, I'm going to add more to this bucket or collection. So it's hello. So for each one of the incident edges, I'm going to consider every one of my incident edges. So I have you, and I'm going to consider every one of my neighbors, okay? We're going to do that, and we're just going to do exactly what I just described a moment. Yeah, you check the neighbors, so we check those neighbors, and now we just want to only count them if they're not marked, right? So that's all we have to do. So if V is not marked, that's the only time we can advance our search, but that's also when we know we're going to have more stuff to count, right? So if our opposing endpoint, or V in our case, is not marked, that means we can advance our search. That means we're going to be more things we can count. So I'm going to update count to be countvert. Whatever the result of countvert is for V, plus the current count I have. I'll get out of the way. And then I just simply return the count when I'm done. So you'll notice that I've written this recursively, but I must stress that the principles still apply regardless if you decide you want to write this iteratively or use a different graph traversal algorithm. I just adapted DFS. I'd like to keep it simple, you know? There's something pretty about a nice recursive algorithm. And that's it. That's how you can count all the vertices in a given connected component, because a connected component will be all the vertices reachable from my start vertex. So this is how I could count up all my friends in my social network if I didn't have that information. It's pretty interesting stuff, right? So you might say, Dan, what do you do about edges? What do you do about edges? So for the sake of variety, what I'm going to do next is I'm going to show you how you can use breadth first search instead to count the edges. Now, one thing I must stress is that edges, it's a little bit more, you have to be a little careful, okay? So with edges, there's something else you have to do a little bit more carefully. So first, you can get away without having to worry about the vertices. However, if you care about the running time of your graph traversal algorithm, it may make a difference. I'll have more on that in a little bit. So here we go. So what I can do is I can just simply take this idea I had over here, where our first here, all I did was I ignored the edges. But now what I would do is I just take those into account, but I don't really care about what the edges are labeled as. I just care that I count it. But for the sake of maintaining the same time complexity, I'm going to also incorporate this idea of marking. So what we're going to do is I'm going to show you how I can adapt BFS to do this. So let me show you what I mean. So I'll just mention that likewise, we can count the number of edges. The number of edges by labeling edges. And only counting unlabeled edges. So when they're unlabeled, that's the time to count them. So just as an example, let's do this with breadth first search. So let's take the same graph I had over there. Just because I want to be consistent with you. So let's see what happens. So suppose I start off at here. And what I want to do, and now I must stress that with BFS, we have a queue, right? We're going to have a queue. And just to make this easier for us to keep track of, I'm going to number the vertices. I'm going to number those vertices. Yes. Now, BFS is quite versatile for the things that you would like to have. As I mentioned previously, you have things like shortest path trees that you can compute with BFS. It's wonderful. It's wonderful stuff. But like I said, you always got to be a bit particular about what exactly you need the algorithm to accomplish, depending on what your graph looks like. Because sometimes if you have a very, what we call bushy tree, very bushy graph, meaning it's very dense along the places that you're only going to be examining, you may want to consider taking a depth first approach only if you really know exactly where you want it to go. If it's very bushy, like at the beginning, like if it's like lots and lots of vertices, high degree, you may run into it quite early on, so breadth first search might be your friend there. If you know it's just, the vertex is really far away, you might have to take your chances with DFS, but either way in practice, you'd kind of pick which one makes sense for your application. But most certainly from a time complexity standpoint, it doesn't make any difference. Just the thing is they have nice properties, different ones. So let's have a queue here. We're going to start off at 1. So 1 gets placed in here after I mark it. So I've handed over to the goblin. The goblin's got, I got vertex 1. Yes. So we're going to take it away from the goblin now. So we're going to take it away from the goblin. We're going to dequeue it out of here. And we're going to consider our incident edges. So we're going to have a tally of how many edges we have. Remember, these are the interconnections between the vertices. So I'm going to now increment this whenever I count an unlabeled edge. So in this case, I pull out 1 and I look at all my incident edges. I'm going to take 1 step into the graph. So I consider this edge here. I'm going to just label them with the word counted, just to keep it simple. So notice that I have counted 1 here. I'm going to mark 2. I'm going to enqueue it, enter it into the rear of the queue. It's going at the back of the line. And then we consider each one of these. Now I must stress them again, as long as it's an incident edge, it doesn't matter which order you take them in. So the fact this is a 2 versus a 4 versus a 3, it doesn't matter in terms of the algorithm. When you implement it, most times it'll be based on the index or how you store the vertices, what order they're in. So same idea here. I put in 4 into the queue, back of the line. I've already marked it. And that increments my counter. And same idea here. 3 goes in here. Increment my counter. And now we're done with 1. It's gone. It's gone, everybody. It's gone, everybody. The goblin's going to take 2. We're going to take it away from the goblin. We're going to try taking an extra step into the search to get away from the goblin, okay? So let's see. So now we got a 2 here. So now this one's already labeled, so I'm not going to count it. We have this edge. That's already marked, so we know we're not going to put 3 into the queue, right? I must stress, however, it doesn't make any difference if you did this, except it will make the algorithm take a bit longer. I'll have more about that later. So now I have 4 edges. Again, I don't have anything to place into the queue. Now we're up to 5 edges. And now we're done with 2. Next, let's go to 4. Goblin takes out 4. Let's take it away from the goblin and run it 1 step away in the search, okay? So let's see. This one, we haven't accounted for this yet. However, 3 is already has already been marked, so we know we don't need to examine that one. So now we're up to 1, 2, 3, 4, 5, 6. So far, we're up to 6 edges. And now next, let's consider this edge. That's not in the queue yet, so let's put in 5 at the end of the line. Increment our counter. And let's do 6 next. So that goes up. Now we got 8. And now we're done with 4. And now let's pull out 3. So DQ 3. All of its incident edges are already labeled, right? So we're done with 3. So keep in mind, you would go through each one of these and see that they're not labeled or labeled. 5, same idea. 6, same idea. And we're done. So now I have 8 edges. And notice that I've just adapted my breadth per search to be capable of doing this. And all I really care about is that the edge is counted for. So I just label it. I don't care if it's a discovery or forward edge or a back edge or a cross edge. And well, BFS would be specifically in our cases forward edges or discovery edges or a cross edge. So let's write out what this would look like. And I'm going to adapt BFS for this just so you can see what we just did here. So I'll walk you through the thought process here. So here's the algorithm. We're going to call it count edges. And it's going to have a starting vertex we start at. The input and output, similar to what we have over there. So I'm just going to, for the brevity of time, we're just going to skip over that detail. The point is it's going to count all of the edges that are reachable from my start vertex. So these are going to be on endpoints of vertices I can reach. So in BFS standard, you're going to initialize an empty queue. We're going to start off with an empty queue. And then we're going to enqueue in the source or start vertex. We're going to enqueue that in. And then we're going to mark, let's mark U. Not you, I'm talking about that U. Then, while the queue is not empty, meaning that we still have a vertex that we have not yet processed all of its incident edges yet, we're going to do as follows. So while the queue is not empty, meaning that we have another vertex in line, if this is the case, we're going to do the following. So first we take out, remember this is like when I was saying about the goblin taking it out from the front. So we're going to process the vertex on the front of the line or our queue. So we're going to dequeue off the front of the queue. That's going to be V. And then we go through our incident edges. So for each edge, VW, we're going to do as follows. We're going to do the following. Now, we have to be a bit careful here because remember, we're trying to count the edges. Now, as I said previously, we're just going to allow it to still continue to mark vertices, which I think will be a good idea for us if we want to maintain the same time complexities, as I'm going to mention in a moment. We're going to check if that edge is not labeled, because we don't really care about it if it's not. If VW is not labeled, then let's proceed. Let's proceed now. So now we know VW is not labeled. So that means we're going to increment our count, right? Because we're going to label that edge. Oh yeah, there's one thing we haven't done. Remember, we still have our counter. This is something we need to add into our BFS. So we're going to put a counter in. Remember, we need our counter, so let's add that in here. It's important, otherwise we're not going to be able to count things. So let's see. We got a count. We're going to increment our count, right? Because we have a new unlabeled edge to consider. So we're going to increment that by 1. Then we're going to label it as counted. As counted. And then lastly, if the opposite endpoint, sorry, I'm getting very excited here. If the opposite endpoint, W, is marked, then we don't do anything with W, right? If it's not marked, however, that means we have more graph to explore. That means it's going to go right into that queue at the end. If W is not marked, then we got q.nq, so I'm going to nq in W, and we're going to mark it. Mark W. Now let's make sure I got all my closing curly braces, okay? Got 1, got 2, got 3, and I think I need a 4th one. 4, and at the very bottom after the 4th curly brace, we're going to return the count. What's V and W? That is the incident edge. That's the incident edge. So when I look at VW here, so notice all I'm doing is I'm going through, like if I was over here back at 1, each one of these would be, this would be V at that time, V, and this would be W. So I would have VW, 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 like this. So they're just that's just an incident edge. So what I'm saying is you are going to label that edge as counted, and we look at the opposite endpoint. That's an excellent question. So all you do after that is you just return the count. That's the last step in this whole process. Hopefully that is clear. Are there any questions about that? I know that the writing's a little bit small here. I had to judge this in my head to see how much we could fit in here. Are there any questions? Don't be shy. But yeah, no, so notice here that this will just ensure that whenever an edge isn't labeled, that we label it. We increment our counter to count for that edge that we just labeled. And if ever we have more stuff to explore, more vertices to expand our search on, we do when we haven't put them into the queue. Pretty fascinating, right? So this is one way you can count the connections in our network like this. There's a lot of different ways you could have this graph. Okay, good. No, thank you. No, thank you. I always like to make sure of these things. Okay, so if we're okay with this, I want to show you one delicate detail of why we're marking the vertices, as opposed to our example we had over here, where I just straight up ignore labeling edges. You'd think, oh, okay, well, Dan, can't you just like get away with not marking the vertices? Well, the actual cool part about this is what I'm saying is you can go over to this algorithm here. For dramatic purposes, let me grab a red marker here. The cool part about this algorithm is you can go like this. You can go like that, and it still counts all the edges correctly. So you could cross out that check right there. However, it comes with a penalty if you do it. So this small check over here will save you a little bit of time. So let me show you an example of what I mean by this. So just as a reminder, breadth first search, so the original breadth first search, it would run, if you say give me an adjacency matrix, it'll run in big O of n squared or big theta of n squared. And for an adjacency list, it'll run in big O of n plus m, where n is the number of vertices, m is the number of edges. So if you think about this, you might say, Dan, how did we come up with the analysis here? Now, we had talked about this actually in a previous lesson, but the big thing I really want to point out to you is that in breadth first search, the whole idea is that whenever you NQ or enter a vertex into the queue, we never put it back in again, right? It always gets examined at most once. And that means that whenever you encounter one of these vertices, it goes into the queue, right? And it only goes, so like if I have my bucket over here, when I mark that vertex, it goes in the queue, right? It always goes into the queue whenever I mark a vertex. It goes into here. It goes in the bucket. It's not, as soon as it's in the bucket, when I DQ it, I've already marked it. So all of the things in here are marked. So if I DQ it, it's still marked, right? So that means that I'm going to guarantee you that at most once, you're going to NQ a vertex and it's going to get DQ'd. So that means since there's n vertices at most in a given connected component, you're going to have big O of n many operations for that. That's where this n actually comes from, right here. And then we have m here. This actually is associated with the incident edges over here. So when I compute these, the number of operations it takes me to compute the incident edges, all of those edges that are off my side, if I do this with an adjacency matrix, it requires me to examine a row of the matrix or table. If it's an adjacency list, I have to examine that list. In this case, what happens is you would end up with the degree of a vertex. That's the number of incident edges on a given vertex. When you add up all of those, you end up with what we call the handshaking lemma. The handshaking lemma tells us that the sum of the degrees is exactly equal to twice the number of edges, which is big O of m. That's where this m actually comes from. So let me show you what happens when you break this property right here. So let me consider an example over here. So remember, the analysis, the way the breadth first search operates is it never is going to put that vertex back in there because the whole point is it's going to compute the incident edges, right? So let me consider, for example, a complete graph. That means that, let's consider a complete graph on 4 vertices. That means that, so if you're wondering what a complete graph is it's going to have, every vertex is going to be adjacent to every other vertex in the graph. This is what we would call, in graph theory, we would call this K4. So it's the complete graph on 4 vertices. So you might ask, Dan, what exactly happens in this case if you get rid of that? So if you put this, you get rid of these 2 lines here. So what we're going to do here is, suppose I go through the same process again. Suppose I have you here, like this, and I have my Q. So let's go through the same process. I'm not going to worry about counting here. So let me show you what happens. So you would put U in the, actually let's number these. 1, 2, 3, 4. So 1 would go into the Q, right? And then you would DQ out 1. You would examine all of your incident edges, right? You take 1 step into the graph. So you'd say, consider, because remember, we'll label this. We have 3, which we mark. But remember, we don't care about the marks right now. And then I 2, mark, 4, mark. So right now we have those in there. Now let's pull out 3. So 3 comes out. We DQ that. Well, notice I don't check if it's marked. So if it's not marked, remember, it is marked indeed, but we got rid of that check. So it's going to NQ it anyways. So 1's going to go back in. So 1's back in. 2's back in. Actually, no, wait. No, 1 doesn't go back in because it's already labeled, right? 1's back in. However, 2 goes back in, right? So do you notice that every time I do this, actually what's happening is I lose 1 edge, but then I have other endpoints now that are actually incident on this. There's going to be an edge where each one of these is going to be marked already. However, I'm going to place it in anyways because I have an unlabeled edge. So notice I have 1 here is already, I'm not going to worry about 1 here. However, 2, there's an edge right here. I'm going to count that. 2 goes back in. And then I have 4, right? So 4 goes back in. Then next, 2 comes out. Well, that's already labeled. That's already labeled. However, 4 is, in fact, connected by not a labeled edge like that, right? Do you see how it goes back into the queue several times, right? But remember, each time I do this, I'm still examining each one of the incident edges, right? So I have to go through each one of them regardless, even if it's labeled or not, right? So I would go through 4. Okay, I go through all my incident edges. 2, I go through all my incident edges, but I'm not adding or doing anything at this stage. I'm just checking them. So I have 4, then I have 4 again, right? It's adding extra work that we don't have to do. Now, like I said, it doesn't affect counting the edges. However, this could have an effect on the performance of your algorithm. Okay? Is that clear, everybody? So that's why I have this small little check in here. Even though it doesn't affect the correctness, it may lead you to have some performance degradation if your graph is fairly dense, like a complete graph. So, anyways, that's pretty interesting stuff, right? So that's actually how you can count vertices and edges that are reachable from a given connected component. So you can count what's in your network. Isn't that kind of neat? So let's get the chat open up here. Hi guys, I know I've seen you over there. Yeah, Nintendo Direct, there was that Direct that this morning. That was pretty darn cool. Did anybody else see the, I heard about the Direct. How many of you have watched the Direct today? Yeah, we know we got a whole bunch of fun stuff coming out early next year.
Concha.
We finally got a name for Breath of the Wild 2. Pretty cool stuff, right?
Direct Hoyt. PogChamp.
Oh, yeah, no, pretty exciting stuff, right? Yeah, it's a lot of things. I'm just trying to think of the games that I was like. Obviously, there's Breath of the Wild 2, which now is I guess it's pronounced Tears of the Kingdom. Like, I think that's it. But let me think here. There's a bunch of games that were actually kind of interesting to me. I'm just trying to remember off the top of my head. Obviously, there's Bayonetta 3. That's a given. Let's see. There were some other ones there too. There's some really great games they announced. I know they have the remake of the Kirby game on the Wii. I've already played that game to death, so I don't necessarily need it, although there's some neat things there if anybody's never played Kirby's Return to Dreamland. Definitely some more gameplay tweaks, which is kind of nice. I can't believe can't remember off the top of my head. There was actually some pretty neat ones that were coming out early next year. But yeah, no.
People speculated this name is why it didn't air in UK due to Queen.
Oh. yeah, that's right. That's right. Yeah.
WLUL.
Oh yeah, there's that too. That's right. Oh man, no. Dang, yeah. I'm just trying to think off the top of my head. There were actually a couple of games that look really interesting to me. I was just trying to think of which ones to discuss here. Obviously, there's the second Breath of the Wild game. There's it's Bayonetta 3. That's coming out next month, which is pretty exciting.
Pikmin 4. Kirby Return to Dreamland remake.
Oh yeah, there's Pikmin 4. That one might be interesting. I know that I had fun with Pikmin 3. The question is, what exactly are you going to do with it? Because I know they're changing up like the perspective, so it's more from the Pikmin's perspective, which is kind of neat. I like that idea. But it was a smaller game I was looking at. It was pretty neat.
Pikmin game that's like Pokemon Go.
Oh yeah, there's that one. But I can't remember off the top of my head. If I remember, I will definitely mention it. That reminds me, I'm going to erase the boards here while we keep chatting. But yeah, no, so far we got, we got some pretty exciting stuff coming out, which is great.
Good. The Fox game.
Oh yeah, the Fox Zelda game, right? It's funny, I was like, when I was talking to Shireen about this, I'm like, oh, that's the furry Zelda game. It looks really cute. Sorry, I was just joking around, of course. But It looks great. I like the visuals and all that stuff. There's honestly a lot of good games coming out soon. I'm just trying to remember which one it was really like grabbed my attention. It's not as popular as the main ones. We have a lot of...
2 of my buds have already played and said it's good.
Yeah, no, that's what I've heard. I've heard it's pretty darn good. That's one thing I always gotta say, especially when it comes to smaller development stuff, always support them, you know? If you think it looks great, give it a try. That's one thing I can always say, especially about projects like that.
There's a Final Fantasy rhythm game called Theatrhythm.
Oh yeah, there's that too. That has so many songs in it, that's insane. It's like hundreds upon hundreds. I think it was like 400 or 500? How many songs was it going to be in that one? I think it was definitely in the order of hundreds. And then they were going to have like an expansion pass and stuff for it. Which is quite something, right? Let's see here. Either way, there's some pretty exciting stuff. If I can remember what game it was that I was really like looking at, I was really hyped about, other than some of the ones we've mentioned here.
Remake of another Final Fantasy game. Can't remember the name.
Yeah, there's yeah, I can't remember off the top of my head, but I know there's a remake of Rune Factory 3 coming out. I'm not Shireen's much bigger into Rune Factory, but she knows all about that one. But she said it's pretty good. But I'm just trying to think off the top of my head. There was one game that looked at me like, oh man, I totally need to get that. And other than the ones we've mentioned. I'm having a brain fart at the moment about it. Yeah, there was a lot of farming sim games. There's a lot of farming sim games that came out. There was a lot. But yeah, no, we got the Zelda game, and yes, it is coming out. The date they have is May 2023, which is pretty darn psych. Though we have to wait a little bit longer, but I'm hoping that it'll be worth it. I know that for me, when it came to Breath of the Wild, I had a blast with Breath of the Wild. For me, it was more of like it was worth the journey. I'm not sure about the climax. Like for me, I was hoping for a little bit more, but then at the same time, if you think of it more like a reimagining of the first Zelda game, then it makes kind of sense that it would be the way it is. Even though it's not technically, but you get my point. But it's a fun game, so I'm hoping that see my thing mostly, like this is me just rambling now, is Breath of the Wild. Things I would really like to see in the next game are dungeons. Bosses with unique gimmicks that require you to use certain things, as opposed to feeling more like
more dungeons, if you get what I'm saying.
Yeah, no, I would like proper dungeons, you know? Do you know how amazing the idea, like, just the setup for a lot of the dungeons are like, but if they were, like, properly set up like your traditional Zelda dungeons, like, that would be pretty darn cool stuff. Like imagine you have, like, your puzzles and all that stuff, but you have it where it's, I don't know the best way I could put it, like, I like the shrines of Breath of the Wild. They're fun, but like I need like proper like those like just the feeling of walking into a place you have no idea what could be in there is something that I really was looking forward to seeing in Breath of the Wild, but we didn't get that. So I'm hoping that we'll get something like that in the second one. That, and I would really love to have unique items again, you know, for like dungeon specific ones. I get the idea why they had to do it the way they did in Breath of the Wild. It's sort of like, oh yeah, no, you have it where it's all like the journey is whatever you decide you want to make it. So, which is a pretty neat idea, but obviously it comes with its drawbacks. So it'd be nice to see where they can kind of like bring some more of those traditional Zelda things. Like that's the kind of stuff I really just love. I know that I've actually been playing on the stream a whole bunch of Zelda games in the past, so I've been playing a lot of the Game Boy ones. So it'd be nice to get a good feel over that kind of stuff again. I was actually I can't remember how many months ago it was. I played through all the Oracle games. So I did Oracle of Seasons and Oracle of Ages. And I actually did like a proper Link game, which is pretty darn rad. Oh man. As a total aside, I remember having to go through Jabba Jabba's Belly twice. And I must stress, for those that have not played Oracle, like the Oracle games, Jabba Jabba's Belly in the Oracle games is a lot tougher than the one in Oracle Ocarina of Time. It's much more puzzle intensive with water levels and stuff. So it's kind of like if you took the water temple in Ocarina of Time and you combined it with Jabba Jabba's Belly and made it 2D. So it's...
I agree.
either, but it was hilarious. Live on stream, I had it. I'm not even kidding. Where the game froze because I was running it through one of my Raspberry Pis. Because I want to have the resolution for the game. Because obviously I have like Super Game Boy and stuff, but it's just a lot crisper for the audience. I think it's a lot better, at least in that sense. It's not as authentic, but it's most certainly it looks better for the audience. I'm not even kidding. We got to the very end of the dungeon and the game froze. It's amazing. So I had to go through the whole thing, and this is what it invented on my streams, the gimmick of saving frequently. It's the rule of the stream is always the save.
Not like this.
It was amazing. It was like immediately we got the MacGuffin at the end of the dungeon, and then it started fading out, and with the whole epic music, and then it just like freezes right there. So we had to go through the entire dungeon. So it was more of like a speed run when I went through the second time. The first time it took a while, but the second time, once I knew what I was doing, I think I went through and got through there. It had to have only been like half an hour or something like that tops. It was pretty fast. But yeah, no, it was pretty... Either way, there's a lot of stuff to get excited about, whether it be games we mentioned or ones that aren't there. I know that Shireen is wanting to try out the Harvest farming game that Square Enix is putting out, the Harvestella, I think that's what it's called. Because she's a big fan of like Rune Factory and those kind of games, specifically like Rune Factory because it has like combat and everything in it. So maybe that one might be pretty cool. I know that I've at least been pretty blessed with a lot of the games we've gotten out this year. Though it's a little bit of a mixed bag. I know that for me, like Shredder's Revenge, that was pretty darn awesome. I'm a huge Xenoblade fan, like huge. Though I will tell you that while 3 is a great game, I didn't like it as much as I liked Xenoblade 2. Though I know that experience and mileage will vary between people. I loved a lot of things about 3 though. It just, without spoiling anything, the ending the end game is a little undercooked. But other than that, it's pretty good experience. Definitely leans a lot more on Western sci-fi. Like a lot of the stuff they kind of take and use in the plot is very Western sci-fi. So it's got a lot of like you can if you're not very familiar with sci-fi, you're like, oh yeah, that's kind of like Logan's Run there. That's kind of like Blade Runner over here. That's kind of like it's really neat. Though some would argue saying, hey, look, if I can identify those things in the game, maybe that's not the greatest thing, but I don't know. It's more of a game that I would say is more like pick up and put down than, say, the earlier Xenoblade games, because it's a lot of side quests. However, one thing I will say, just as criticism of the game, is for Xenoblade Chronicles 3 is that it's way too easy to get over-leveled in that game. I mean, I'm not even kidding. There was one chapter where I basically fought almost nothing except for the bosses. That's how over-leveled I was, because as soon as you're about 5 to 10 levels higher than an enemy, they won't fight you unless they're specifically going to engage with you. Because sometimes there's enemies that are aggressive, some that aren't. But most certainly, it was kind of frustrating because like, with the other Xenoblade games, I didn't have this issue at all, where like I felt like even when I was doing like 5 or 6 side quests, every time I go to a town or something like that, I felt like I was still getting progress through, and I didn't feel like I was grinding a whole lot really either. In fact, in 1, it's a little bit more grindy, but 2, most certainly not. 3 has a lot of great stuff, but it's very easy to get over-leveled, where like you're like, oh look, there's this stuff over here I could do. A lot of it's built around the way it has this, what it called its hero system. Like, it pretty much rewards you by doing side quests as opposed to giving you things, then using them for side quests. So that incentive structure sort of makes it easier for you to get over-leveled because there's so many things you can do. But it's not surprising. I mean, it's just maybe a flaw of the design of the game. It's a little bit too easy to get over-leveled.
Some other notes I had from
there's the new
emblem, new character for Xenoblade 3. Fist of the North Star boxing rhythm game, Story of Seasons remake, new Mario Rabbids game, Fa Farm, Rune Factory 3 remaster, Just Dance, Bayonetta, Octopath, a martial arts badass that gets old, and GoldenEye hype LOL PogChamp.
Yep, that's what I was going to mention. Is we're going to get a bunch of more retro games on the Switch Online. GoldenEye's in there. We're gonna have online play on that, which is pretty exciting. Yeah, no, you mentioned some other ones. There is that one martial arts game. I can't remember the name of it off the top of my head. That it was a pretty neat gimmick that where like the player gets older, especially as they combat more. That is actually a pretty neat concept. Yeah, there's the expansion pass stuff for Xenoblade 3. It's going to be just another side quest kind of thing, and there's a new mode that's similar to what Xenoblade 2 sort of had. Oh yeah, there's a new Fire Emblem game. That one looked pretty cool. I do enjoy the Fire Emblem games. Yeah, no. Then there's always Just Dance. Just Dance is just this thing that just exists. It's always there. It is sort of like a continuum of Ubisoft. It's just Dance. If there's a console, it's going to have Just Dance on it somewhere. But yeah, no. Why don't we get to our next part of our lesson? We're going to get into something I would argue is a little bit of a fun... I would argue it's kind of a nice, simpler one than the one we just seen. It actually just uses the ideas we talked about just a moment ago. So when we get into that, so let's do this, okay? So, the next application I'm going to show you is testing if a graph is connected or not. So we're going to check if a graph is connected or not. So we're going to see if a graph is connected or not, or we're going to test its connectivity. Now, I want to remind you of a couple of quick terminology things. So, what does it mean for a graph to be connected? So, a graph is connected. So, for graph G, it is connected if the following is true. For every pair of vertices, so any one of those vertices in that graph, there has to exist a path between them. There exists at least one path from U to V. So if this is satisfied, so let me show you an example of a connected graph. So I'm just going to have a bunch of vertices here, and I'll just add a triangle at the bottom. Look at that pretty little triangle. So if you take a look at this graph, notice that there is an edge. So if I pick any two vertices in this graph, there exists a pathway, a sequence of adjacent vertices that can get me from one vertex to any other vertex in this graph. So this graph is connected. However, I can make it disconnected, meaning it's not connected, by simply doing the following. I can introduce two more vertices, connect them like this, or maybe I can introduce what we call an isolated vertex. Notice that now it does not exist a path from, say, this vertex to that one. They're separate. So in terms of connected components, which we're going to talk about at some point, we have 1, 2, 3 connected components. And this graph, by definition, is disconnected. So let me just fix that E there. Just staring at it. It's like, let's fix that. So we would like a very simple test to know if a graph is connected or not. So here's a neat observation. Did you recall when we've seen depth first search or even breadth first search? Do you notice that when we start at some vertex in the graph, do you notice that we'll label all the edges of vertices that are reachable from the start vertex? So we'll get to all of them. So notice that it will mark this one, 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 and all these, but it will not mark those other vertices. That's on a single call of DFS, give it a start vertex. So these are all these vertices and edges are reachable from this vertex. So we actually can use this information as a test to know if a graph is connected or not. So if I fail to mark all the vertices in the graph, we know that it's disconnected. And that's exactly all we have to do to test if a graph is connected or not. So here's just an example of how I can do this. So here we go. So I'm going to call this algorithm connected. So I'll call it connected, and it's given a graph. So it's not given a start vertex or anything like that. It's given a graph. So what I'm going to do is I'm going to adapt the graph traversal of the entire graph, meaning that I'm going to just start this up at some vertex. I'm going to allow it to do a depth first search or a breadth first search. Doesn't matter which one. And we're just after that just going to scan through all the vertices and see if all of them are marked. If they're all marked, then you're good. It is connected. Otherwise, it's not. So as input, we're given graph G. G is equal to VE. So we got our vertices and our edges. And I assume that these vertices and edges can be marked and labeled. And as output, all it's going to do is tell us true if if G is connected. If G is connected. And it's false otherwise. So here's what we're going to do. Now, you can have the same setup we had before that makes sure that the graph is entirely clean, meaning that all the vertices are not marked, all the vertices are not labeled at the beginning of this process. We can introduce that at the beginning of this algorithm if you would like. For the purposes of the time, I'm just going to skip past this. Assume that the graph is what we call, it's clean. There's nothing written all over the graph, okay? I don't have the X's or labels or anything on the edges, but you can add that at the beginning of this. So we're going to just start off by, you just consider any vertex V. So any one. You could be the very first one that you could pull off. It can be anyone. It can be an arbitrary one. You could flip a coin. It doesn't matter. It could be any one of the ones in this graph. Or any undirected graph like this. So then you're just going to run DFS. Keep in mind, if you don't like DFS, you could just put BFS here. Doesn't make any difference. And then all I do is I just go through each one of the vertices and I just check if it's marked or not. For each vertex, V and V, we're just going to do the following. So all we're just going to do is we're going to check if V is not marked. So if V is not marked, then all you're going to do at this stage is just return false. Because so you might say, Dan, why? So suppose that I give you this graph, for example. If I did DFS on, say, this vertex, say U is V. It will mark all of these. And then I scan through each one of them and I check, is this one marked? 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 Oh, that one isn't marked. It means it wasn't reachable, meaning that there does not exist a pathway from V, or U in that picture, to that vertex. So that means it's disconnected. So then you just go through this loop. Gotta add the curly braces. Never forget your curly braces. It's always a good time. Then, once you've examined all the vertices, if all of them are marked, meaning that this will never occur, you're going to return true, meaning that the graph is connected. Piece of cake, right? Let's get the chat open. Yeah, I know. So does anybody have any fun plans this week? I know we're hot right into September. I don't know for you, but summer just sort of zipped right past for me. But But yeah, no, that's how you can test if a graph is connected or not. And it's very pliable. You can just simply just put whatever graph traversal algorithm, as long as it has this reachable property that DFS and BFS has, you can just put it right there.
Jam-packed with weddings.
Oh man, weddings. That's going to be a lot of cake. Oh man. Are they all on weekends, or is it like some of them at least in the evenings? Or during the day on some of them? I know with weddings, man, that could be a whole day's affair, depending on what wedding it is and how big the family is.
Yeah, weekends.
Weekends. So yeah, you're definitely going to be busy with that. I wish you the best of luck. They could be a good time, especially if you know the people. It's a good time. I know that. Yeah, no, weddings, they can be a good time. Especially depending on what the wedding does. I know that some people really go out there with their weddings, so you can get sometimes that's an amazing buffet or something. You just gotta watch your waistline with that kind of stuff. Oh man, no. Let me just erase this. No, sorry, I'm just losing it over here. We're going to be moving into our last part of our lesson here for today, which is pretty darn
back from a wedding, and I avoided the cake cause I could already barely fit into my suit. LUL.
It's the great battle, man. It's the great battle. I got you with that one. Oh no, I know with me. It's always that time of the year, because I know for me, like, there's lots of birthday parties around this time of the year for me, and let's just say you always have to be like, do I want to pick my battles with this one or that one? Let's just say I'm making sure I go for my my at least 4 or 5 kilometer walks almost every day. That's how I try to keep myself in action. Oh man, no, I totally get that one. It is what we call trade-offs in computer science. It is the question of, do you really want that extra piece of cake or that really awesome buffet sandwich or something like that, or that good pasta salad? Or not?
Nice.
Oh.
I'm lucky if I get out to the mailbox every day. LUL.
Yeah, no, with me, I really gotta, like, I always have to set myself aside time when I'm doing this stuff, because otherwise, I know for me, like, at some points, it used to be rather difficult for me to do that, so sometimes I would even go for walks in the evening, when I would have, like, it would just be like, it's like, what other time do I got? So sometimes I'll go out in the nighttime when it's all dark out. I still do that these days, when the mosquitoes aren't too bad here. The mosquitoes can get kind of bad here. Oh man. Oh man, yo, can't believe we're almost to the last thing we're going to talk about here today. We're almost there though. We're almost there. Oh man. Either way, hopefully you have a wonderful rest of your day. I know that once I get this sorted out, I'll have kind of my last round of questions, and if anybody has any fun things they want to chat about, we can do that before I head on out. But we've got one more application, and we're going to have some fun with some props too. So I got to get that stuff out. Oh, let me grab that. Gotta get some props. Got some props. I'm getting things ready for our fun. Okay, so let me get the stuff ready here. Okay, let me just get this out of the way here. Okay. Oh, that's a red marker. How'd that get in my pocket? I guess I must have stuck it in there at some point. I usually keep black markers in my pockets. I have things all over the place in my pockets. Without telling too much about the magic behind the scenes, I got like 3 different things I do all at the same time while I'm doing this. So sometimes if it looks like I'm doing like 3 different things, that's probably because it is. But no. So let's get into talking about one more application here. We're going to talk about how we can compute connected components. So this is another basic application for graph traversal algorithms. Now you might ask, Dan, what's a connected component? So let me draw you a picture of a graph just to kind of help you see what we're talking about here. So in a graph, we can have the concept of what we call a subgraph. So now a subgraph is just a subset of the vertices that forms a graph. So sorry, a subgraph is a subset of the vertices and the edges such that it forms a graph. For example, I can take these 3 vertices and these 2 edges. That would be a subgraph of this graph. Actually, I'm going to add a couple more vertices in here. There we go. So when we talk about connected components, we're talking about maximally connected subgraphs. So what do I mean by that? That means that if I were to include this vertex in a subgraph, it's not maximally connected because so it's not maximal in its size because I can include another edge and another vertex, right? So I would include this in my subgraph, but notice I can also include this vertex and this vertex. So if I include all of those and all of its edges, that would be what we would call a maximally sized subgraph, which would be one of the connected components. So notice that I have one connected component, this one right here. I have another one right here, and I have another one right here. So we have 3 connected components. So the question is, how many do we have? That's one thing we can ask. We can also ask or identify the connected components. So you might ask, Dan, why would we care about this? Now, a very common application for connected components is what we call segmentation. So sometimes this occurs in image processing, for example. So say, for example, I would like to have it where, say, each one of these, like if I imagine I took this graph and I imagine that was a picture, a grid of vertices and edges, where the edges represent connections between non-transparent parts of the image. So you could imagine I want to identify all of the things in the picture. So all of the separate chunks that I have in the picture. So segmentation in this very basic context would be I try to figure out which things are not transparent and which things are they. So I can identify each one uniquely with, for example, a number. So on its vertices and edges, for example. And that's one way you could use this. Is you could imagine it as an image for image processing. You could imagine this, for example, if for example, we're talking about our friends in a big social network where there's a lot of interconnections between them. You can imagine I have, say, 2 friends. I got my narwhal friend right here. So you say, hello, says hi to everybody. And I have my seal friend over here. Now, I would like to know if, say, for example, my 2 friends here, if they belong to the same social network or not, meaning the same part of the network. I should be a bit more precise. The same part of the network, such that if I wanted to find a chain of friends between them so that they can maybe invite some friends over and have pizza, that I'm able to do that. And believe it or not, answering that question is just like answering this question of which connected components do they belong to. So here's the catch though. So suppose that my narwhal friend is up over here, and I say, hey, look, this is connected component number 1. And all of these edges and vertices, they're part of connected component number 1. So my narwhal friend is in connected component number 1. So this is the bucket for connected component number 1. Now, suppose that my seal friend is in this connected component. Now, just for the sake of ease, I'll label this as connected component number 2. And say this is connected component number 3. So imagine I'm going to number the edges and vertices with number 3. So I would have my seal friend maybe in this bucket representing connected component number 3. And if I were to ask, hey, look, can my narwhal friend, does this narwhal friend have a sequence of friends, or at least say the friend of the seal? Is there some way that these two are actually part of the same network? And unfortunately, they are not friends among the same network. At least if we're talking about the connected components, right? Does everybody see that? So if I look at my narwhal friend doesn't have any friends in common with my my seal friend, right? Because they're way over here. So in irony, my narwhal friend and my seal friend aren't actually friends with each other. Does everybody see that? So in fact, they don't know each other either. So if you imagine that there's a pathway that represents my friends that are in common with each other. So you can imagine like I'm not sure if you ever heard of 7 Degrees of Bacon. Like you can imagine we could play a game like that within each one of these connected components to find if we have any friends in common. But unfortunately, my narwhal friend and my seal friend, they don't have friends in common because they are not a part of the same connected component. In fact, there's no chain of friends that I could find, including from the narwhal to my friendly seal. So what I could do now is if ever I wanted to say, come along in my graph, and I wanted to say, hey, look, I have this friend and I have this other friend. Can they have friends in common with each other? I can ask my narwhal friend, hey, look, I'm in connected component number 1, and my seal friend can say, I'm in connected component number 3. The answer will be straight up, no, they do not have any friends in common. Pretty neat, right? So that's one way you can use connected components. So the way that we're going to do this here is we're going to assume that our graph will have these numberings as an extra attribute that we can keep track of with each vertex and each edge in the graph. However, you can easily modify the ideas we talk about here to store, say, a list or some other data structure that has this information baked right into it. But there's many, many, many different applications for connected components. That's just one example of something you can do with connected components as soon as you identify which part is with which. So let's talk about this. So let's assume each vertex and edge can be numbered. And the next thing is that DFS and BFS with a starting vertex or source vertex, has a traversal that processes all vertices and edges reachable from it as in the starting vertex. So you might say, Dan, what are you going to do then? Well, we're going to use the same idea that we had from testing if a graph is connected or not, which in that case, we picked the vertex, we ran DFS or BFS, and then we can determine if there are more connected components or not. If a graph only has one connected component, it must be connected, right? So if we take and we have it where we have multiple connected components, what we could do is we could just simply number each vertex and edge by adapting one of these two traversals so that every time we encounter a new vertex or edge that's a part of that given traversal, we can number it uniquely. So that every time we start up DFS or BFS again with another starting vertex, we assign a new label or number, as we're going to say here. So let's see how this plays out, everybody. So the whole idea is that I need to make sure I label the vertices and edges uniquely among each connected component. So I could say if I grab you one vertex here, I should be able to tell you this is in connected component number 1. Just like when I had my narwhal friend and my seal friend, I should be able to tell you that these two people are not, or I say animal friends, aren't actually friends with each other, right? They should be able to tell you that they belong actually to two different ecosystems, I guess. So let's see here. So let's put this all together. Sorry, I'm getting very excited here. So what we're going to first do is we're going to adapt the same idea that we had previously from our test for connectedness. Except what I'm going to do is I'm going to start off with a number, and every single time I run DFS or BFS, I'm going to increment this counter by 1, so I have a unique number each time I invoke it. And then I'm going to have it where I modify one of the two traversals such that I pass along this number, and every time I'm going to encounter a new vertex that gets marked and a new edge that just gets labeled, I'm going to number it. Okay? So this is, in the most purest sense, I'm literally going to adapt these two types of traversals in a specific way. But also I want to do this in a way such that you could still apply BFS or DFS without any modification. So all we're going to do is we're going to add this extra attribute in so that it's no different than DFS or BFS, with the exception that we're going to focus in on this numbering, okay? So we're going to have, our algorithm is going to be called comp with 2 N's. And it's going to take in the graph. And as input, we're going to get a graph G. And I must stress that the number, it's assumed that the vertices and edges are able to be marked and labeled respectively, and that the edges and vertices can be numbered. They can be assigned a unique number like in our example over here, based on their connected component number. Output is going to be to identify, so it's not going to actually return anything other than it's going to modify the graph. It's going to change these attributes on each vertex and edge. Identify connected components. That's what it's going to do. So you could have the cleanup phase at the beginning of this algorithm if you'd like. I'm just going to, for the sake of brevity, just straight up cut right into the whole process that we had, just akin to a previous example we did. So we have a variable I'm going to call comp num, which is going to be the component number. We're going to assume that the first connected component is labeled 1. So like in our example here, I started off with 1. And then we're going to go through for each one of the vertices. For each vertex V among the set of vertices, we're going to do the following. We're going to check if V is not marked. If it's not marked, what did we say? It means that there's another connected component out there. So if V is not marked, sorry, that looks like an R. If V is not marked, then you're just going to update our, sorry, instead of updating, let's just first run connected components, or comp. We're going to run it with vertex V, and we're going to give it that number that we currently have, comp num, and then we're going to update comp num to be incremented by 1. So comp num is going to be comp num plus 1. And that's the end of the if statement, and that's the end of the for each loop. And there you go. So you might ask, okay, so what's this now? Because it takes in a vertex and it takes a number. So now this will ensure, so I must stress, just really stress this point, and we've seen this when we talked about testing connectedness of the graph, is that if the graph is connected, every one of the vertices and edges will be labeled with a number 1, okay? So they'll be numbered 1. However, it's disconnected, it means it has more than one connected component, so this may get run several times. The point is, it doesn't change the overall nature of a depth first search traversal or breadth first search traversal. In our case, I'm going to adapt DFS, okay? So let's see how this is going to work out. So we're going to adapt DFS just to keep this really simple, I'm just going to say adapt DFS. Because I think I got the core idea across. So here we go. So here's the algorithm. We're going to give it the same name, I know, Dan. You're funny. It's going to be called ConComp, except the parameters for it are going to be different, which means it's okay for me to do this. So I'm going to have a vertex U and a number called CompNum, akin to what we just said over here. So I'm going to skip over the input and output, but it's going to identify the connected component for vertex U. So all the vertices and edges that are reachable from vertex U will be numbered CompNum. So what's the first thing we always do in a depth first search? Well, we mark the vertex, and then now I'm going to introduce this numbering. So I'm going to have a function. It's going to be number. It's going to take in a vertex, and it's going to apply a number to it. That's what number will do. So it numbers vertex. So it numbers the vertex. That's all it does. There's nothing else. It's just like a one-liner in there. So next, we ask, well, we don't ask. We just simply go through each one of the incident edges, just like we did before. For each edge UV, we're going to do the following. We're going to check if the edge UV is not labeled. If UV is not labeled, then we better do something. Then, because it's not labeled, I'm going to number it now. So we're going to number it. So I'm going to have another function called number. It's going to take in an edge, and it's going to take in a number. So I'm going to give it U, V, and it's going to be CompNum. So all this is going to do is number the edge. There's nothing magic going on here. That's all it is. It's like a one-liner. That's it. There's nothing scary or anything happening inside of this. It's just some constant amount of operations that happen here. So it numbers the edge. Then we just do the same thing we did before. If V is marked, then what we do is we label UV as back edge, right? Otherwise, we're going to label UV as discovery edge or forward edge. That says discovery, by the way. The V and the E and the R sort of melted into each other like it went in the microwave, like microwave cheese that went a little too long. And then we're going to apply ConComp with V, and we give it CompNum. The same number. We don't change the number. The only time we change it is when we have a new connected component. Yeah, exactly. So we just run it like this. This is it's not much different really at all to how DFS was originally set up the way I had it before. Just now I have this numbering going on. And I just renamed the function. And there you go. So all I did was I took DFS and I just tweaked with it ever so slightly. So I added this additional behavior to it. So with this, I can number my connected components so that all I have to do is if ever I pick up a vertex, I can say, hey, look, which connected component do you belong to? I'm number 1. Or, like my narwhal friend says, I'm number 1. And my seal can say, I'm number 3. But the point is, now we have this all set up so that if ever we have a query about which connected component it belongs to, we have a unique label or number, as we have done, for each one of them, okay? So that way, if ever I need to point at and say, hey, look, is this Does this belong to the same connected component as that one? Just like when we talk about my application about segmentation just briefly, notice that now I have a way to say, hey, look, say I have a group of pixels. I don't know, say I have like this. So say I have, say some pixels here. I have some pixels there. And I have like 1 pixel down here. What you could do with this is if you can model this as a graph, where what you do is you would take each one of these and you'd say, hey, look, there's an edge between 2 vertices. If they're connected by, they're both, first, they're not transparent, but they also are adjacent to each other. So you can imagine it like I have this, then I have 3 down here, or you can, like, I must stress that you can easily adapt this so all of these blank spots are also vertices and edges. Just that you might be interested in the ones that aren't transparent, the ones I shaded. So this is a way I could represent these pixels as vertices and edges in a graph. And if I wanted to ever ask, hey, look, does this, like if I pick one of these pixels, if it belongs to that coordinate and I ask, okay, does it belong to this chunk, or this chunk? If I label these as connected component 1 and 2 and 3, I should be able to tell you if this chunk belongs to the same chunk as this one or this chunk belongs to that chunk. Does that clear everybody? So this is one way you can use connected components like this. You can use it in much more sophisticated analyses like for one, if you have the connected components, for example, you could build a graph like this. So what you do is use the graph traversal approach like this, where you label the edges and vertices. You just add additional checks, for example, to check, oh, does this pixel have an RGB value of, say, a certain threshold? Then you would include it as a vertex, and it belongs to this, say, one component over here. This one. So the point is that it gets, I'm encouraging you to think about the graph not just as just a graph, but also as something that you can use as a tool for modeling all sorts of different things. But yeah, so this is one way you can use connected components. You can help you organize chunks of your graph so that you know which part belongs to which part. Just like if you imagine these as, say, neighborhoods in the most literal sense, like here's a bunch of houses. I don't know, I'm like Godzilla here. I'm just like, I'm just coming over here. And this is one neighborhood, that's another neighborhood, this is another neighborhood. I should be able to tell you if I smash this neighborhood, but I leave this one free, okay? So, anyways, that's how you can connect, sorry, this is how you can compute connected components, everybody. Sorry, I'm getting really excited here. Hope you thought that was pretty interesting. So let me get the chat open. But yeah, no, so this is what you could do to compute.
To old school SimCity.
Oh yeah, no, so if you ever wonder like how, for example, somebody could say in like something like SimCity, be like, hey, look, I have this neighborhood. What they could do is have a very simplified representation of what like different parts of the city are. And say if they're interconnected, say by a train or a street or something like that, and you want to ask a question of like, okay, is this road connected to that hospital over there or something like that? So you know that they're going to be bridged off like that. You could use a graph like that to model this sort of stuff. So the interconnections between things that are relating over the city. This is one way you could do it. There's many ways. I don't claim that this is how they do it in SimCity, by the way. I haven't looked at their source code or anything like that. I imagine it was quite sophisticated for its time. Even then, this is some pretty bread and butter kind of stuff for graph theory, which is pretty neat. But yeah, no. So connected components, and probably the neater applications I've seen with connected components other than this are, community detection. Like say if you have like a bunch, like you have some definition for what belongs to a connected component or not. So you'd build the graph in this way, and I would like some way of labeling that as a community versus things that aren't. So this is one way. I've seen it in like image processing where like say people want to do like fingerprint detection. To identify the parts of the fingerprint, you compute things like connected components using thresholding on like kind of like what I talked about here about the pixels. You can identify the chunks of the picture into connected components, and then you can ask the question of, okay, is this part about this part? So if they're similar enough, what you can do is you can combine them into a larger connected component. And you can think of it like that in terms of clustering. Like is this close enough related to this? So then I should merge these two chunks. So some people think about this sort of stuff as well in terms of what they call for forming a cut on a graph. So sometimes people like to think, okay, this part's similar to that graph, so this part of the graph, so I'll combine these two pieces. This is sort of some discussion that people will have about classifying. If you're thinking about like machine learning, by no means am I a machine learning kind of guy, but most certainly if you're curious about like, okay, this belongs to this versus that, there's a mixture of geometry and graph theory that makes a lot of that work. But like hypergeometry, not just like flat surfaces, like multiple dimensions of things to determine if there's a cut in a functional space. But if you overly simplify it into a graph-like representation, like where you just care about the connections, there's a lot of things you could do. But either way, this is just me spitballing ideas at you, because I always like to get people excited about this sort of stuff. But yeah, just in your dreams, don't think about me as Godzilla, okay? Save yourself some grief for later. But yeah, no, are there any questions or anything like that? Don't be shy. I'm pretty happy to answer any questions, or it doesn't even have to be about this specifically. One thing I will also mention while people are thinking about things to ask is that on Thursday, I will be streaming. I'll be doing a game stream. Right now, I'm somewhere in between thinking of playing a... What I was thinking about was either I'm going to be playing a Sonic fan game or another Mega Man game. I'm not quite sure which of the two. I am quite tempted because I've been playing the Mega Man Game Boy games. I played Mega Man 5, then 4, then 3, and last week I played 2. Maybe I should play Wily's Revenge, seeing as that's the only Game Boy Mega Man game I have not played yet, at least on the stream. So I don't know. Maybe we'll see if that's the one I'll play. But I think that might be a good idea I do that, seeing as it would be a matter of consistency, because I've been, other than 5, because 5 I did a little bit while ago, I've been going down from 5 all the way down to 1. And 1 is the only one I haven't done. For those that are unfamiliar with the Game Boy Mega Man games, they're a whole other beast. I highly recommend checking them out. Especially Mega Man 4 and 5 on the Game Boy. Those ones, if you've never played them before, seriously, give it a shot. They are a whole other beast if you've never seen them before. Like the whole thing with the Game Boy Mega Man games is that it's sort of like half and half. It's like coffee and milk, and like, oh yeah, look, Mega Man 2 on the Game Boy has half of them are Mega Man 2 Roll-Up Masters, then there's half that are Mega Man 3 Roll-Up Masters, then Mega Man 3 on the Game Boy has the remaining half of Mega Man 3 Roll-Up Masters, and it has half of the Mega Man 4 Roll-Up Masters. Then Mega Man 4 on the Game Boy has the remaining half of the Mega Man 4 Roll-Up Masters, and then half of the Mega Man 5 Roll-Up Masters. However, Mega Man 5 is a whole other beast in its entirety. It has the Star Droids, which is a whole other cool concept on its own. That game, I would consider that if you ever could get your hands on playing that game, do it if you've never played it before. It's worth the experience.
I hadn't played the Game Boy ones until I got one of those compilations on 3DS, I believe.
Yeah, no, because I know on the 3DS you can buy them in the store for really cheap. That was actually one of the few ways that like you can officially play the games, other than obviously getting them on like Game Boy. But most certainly, if you can ever get your hands on them, they're a great time. If my recommendation is usually goes up from 5 down to 1. So 5 is my most recommended, 1 is my least recommended. So like 5, definitely if you like playing Mega Man games or want to play a good Mega Man game that isn't like the NES ones, but it still has the same vein of it. 5 is really good. 4 is really good. It's got cutscenes and all sorts of wild stuff in it that the NES games don't even have, which is kind of wild. It also has one of the largest, like, retro-style Mega Man final bosses. Has one of the largest ones, which is pretty darn cool given it's a Game Boy game. That's the one with the Wily Golem. Mega Man 3 on the Game Boy. That one's... It's a little rough around the edges, but it's generally pretty good. I would still play that over even some of the NES games. Even though the NES ones I really like too. But The only thing that really sucks about Mega Man 3 on the Game Boy is they didn't really quite get over the hump of screen crunch. So what they did was the games are all designed so that they fit on the screen, but obviously the big issue is that you don't want to have it where enemies are just flying at you from side of the screen without you seeing them very easily. And they got really aggressive with shield attackers. Like, those are the enemies with like the little shield. Let me just doodle it. It's these guys. The ones that look like this, where it's like, oh yeah, there's a shield. They have little eyes like this. I'll give them suspicious looking eyes. Where it's like this, and then it has like a little booster like this. Yeah, I gave them the really suspicious looking eyes. The shield attacker's up to something weird, man. Sorry, I'm just losing at this. Just add the music, just go dud, just like dud, then add the eyes go back and forth like this. But no, these enemies are the worst thing in that game. It's because they in Drill Man stage is probably the
hit from the back.
Yep, yeah, the ones you have to hit from the back. But the thing is, in Drill Man stage, for example, or Dust Man stage, it just sort of just come out from the end, but you have no time to react. They come pretty fast. But that's the only thing I really could qualm, other than some of the pits are a little risky in Mega Man 3 on the Game Boy. Other than that, I could recommend that game. It's got Punk, the Mega Man killer, in it. Mega Man 2 on the Game Boy. It's my first one I played, but it's definitely the black sheep of the Game Boy games, but it's pretty cool. It's pretty cool. But yeah, no. If there aren't any other questions or anything like that, I think it's best I stop things here. But most certainly, if you find yourself around, probably a Thursday evening, like I'm talking like in the Americas, because I know, for example, I have some viewers that watch this like in Norway and that, like my lovely friend Tor. Usually around in the evenings, though I've been trying to do it a little bit earlier as well. If you find yourself wanting to watch me play some games and have some fun doing that, check me out on Thursday. I've been doing live content on Tuesdays like now and Thursdays. And of course, if you really like this stuff, make sure you follow, like, tell your friends to come on out. Seriously, we have ourselves a good time here. The more people we can have on out, the more of a blast we get to have. But if you enjoy this content, be sure to subscribe, follow. Of course, tell your friends, like I said. And of course, check out my Patreon, patreon.com/pagewizard. All the notes that I have prepared that are part of this lesson, they are all going to be available there after today. Well, later today. Other than that, I am currently working on the website for pagewizardgames.com, so you can check out that when I have that available. Right now, it's sort of just got a linker thing right at the beginning.
I only caught the second half, but it was interesting stuff.
No, anytime. We're doing live lectures like this almost every Tuesday, so I'm planning to do another lecture like this next week on Tuesday. It depends on one thing. I'm planning to do one next week, but I might be attending a conference. I'm not quite sure yet. But I will let people know. I usually on social media, on my LinkedIn, Twitter, just take a look for the description of that. And yes, that was a fly that flew across the camera if you've seen it. There's a little thing that went like this. That was a fly. It was rather looking like a lot bigger because it was quite close to the camera. Sorry, I'm just losing it here. But yeah, no, check out my links. There's a lot of ways if you want to watch this replay afterwards. You can check it out on Twitch for a little bit, but it'll be on YouTube. And of course, if you want to see more daily CS educational content and more, and a lot of fun stuff I do, check out my YouTube, Page Wizard Games, Learning and Entertainment, or just search Page Wizard. And that being said, I want to say thank you so much for coming on out. It was a blast. And have yourself a beautiful day. I'll see you later.